I will also check. Yeah.
Yeah. I got the message. Live streaming started.
Yeah.
Okay, start.
Okay. So, good afternoon, everyone. I'm Dr. Rohini Lakshman Bhatt, working as Assistant Professor in Department of Atmospheric and Space Sciences, Savitribai Phule Pune University. I welcome you all to the Atmospheric Dynamics and its Applications to Climate Sciences weekly online lecture series, inaugural session. It's a privilege for SPPU to host this series with SAMA. Now, I would like to introduce our Honorable Vice Chancellor, Sir, Professor Dr. Suresh Gosavi, Sir, before he gives his opening remarks. Professor Dr. Suresh Gosavi is currently working as the Vice Chancellor of Savitribai Phule Pune University, Pune. He has more than 30 years of teaching and research experience. He has worked on various academic positions such as Director, School of Physical Sciences, Director, School of Basic Medical Science, Head, Department of Physics, Head, Department of Environmental Science at Savitribai Phule Pune University, Pune. He has also worked as a visiting professor at the Université de Franche-Comté, Besançon, France, King Saud University, Saudi Arabia, and the University of Melbourne, Australia. He is presently working at PIRC Tokyo, University of Science, Tokyo, Japan. His research interest mainly includes nanomaterials and nanotechnology systems and applications, besides nanocapsules and targeted DNA vaccines for immunotherapy of cancer, micro and nanofluidics, and solar thermal technology for rural electrification. He has supervised 26 doctoral and 16 MPhil students, besides mentoring 14 postdoctoral fellows. He is fellow of Maharashtra Academy of Science. Professor Gosavi is on the editorial and reviewer boards of several journals of repute. He has published 305 journal articles and so far and has 8 patents to his credit. Sir, I would request you to give your opening remarks.
Okay, thank you, Dr. Rohini, for kind introduction. On behalf of Savitribai Phule Pune University, I welcome all the delegates, panelists, and the member of South Asian Meteorological Association for the lecture series, which is jointly organized by SAMA and Savitribai Phule Pune University. Savitribai Phule Pune University is one of the premier state university in the Maharashtra, which is the second largest, and we have 56 departments on campus and around 800 plus colleges affiliated with us. At one point of time, we have 750,000 students. We are the only state university which has opened its offshore campus, and since last year, we have been running our Qatar campus in Doha. As far as the our powerful academics and thought leadership is concerned, okay, which has brought us in the NIF ranking, and in the recently declared national ranking framework, okay, we are third in the state university in the entire country, 23rd in the university category, and 37 overall in this. In QS ranking, which is declared recently, we are in the bracket of 500 to 550, and in Asian ranking, we are 173. This is what we rank ourselves. We have inclusive, equitable, holistic, and affordable education, which we are providing to the society. And the hallmark of Savitribai Phule Pune University is its inclusive, tenacity, initiative, plurality, and integrity. This is what our hallmark is. As we know that this SAMA is a non-profit society representing 9 South Asian countries, which is promoting meteorological science for sustainable development and citizen well-being, which is established in the year of 2020 and has 700 plus members and has conducted global webinar, workshops, and 4 extensive lecture series. In collaboration with Savitribai Phule Pune University, a premier institution with renowned Department of Atmospheric and Space Science, which is established on campus, which is totally supported by Government of India Ministry. And now this lecture series, which is being organized, in which they will be discussing on atmospheric dynamics and application to the climate science. On behalf of Savitribai Phule University, I welcome you all and hope that this lecture series will reach to the society in true sense, wherein the new generation, which will be getting joined through this to the premier institute like IITM, IMD, and the institute which are really dealing with the climate science and climate things which are very important nowadays. Okay, not only in the country but also worldwide. Okay, with this brief note, I welcome you all the panelists and the member who have joined online to this lecture series. Thank you.
Thank you very much, sir. Now, I would request Professor Someshwar Das, sir, Secretary of SAMA, to please give his welcome address.
Thank you, Dr. Rohini. Professor Dr. Suresh Gosavi, Vice Chancellor of Savitribai Phule Pune University, ABM retired Professor Ajit Tyagi Sahab, President of SAMA, Dr. Jaman Chaudhary Sahab, Vice President of SAMA from Pakistan and former Director General of Pakistan Meteorological Department. Today's distinguished speakers, Professor UC Mohanty, former professor at IIT-Delhi and IIT-Bhubneswar, and presently the distinguished professor at the Center for Climate Smart Agriculture, SOA. Dr. P.N. Sen, former Deputy Director General of Meteorology of IMD, members of the organizing committee, distinguished participants from more than 47 countries, ladies and gentlemen. I welcome you once again on behalf of the South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University, India. As you know, this is our 5th lecture series on atmospheric dynamics and its applications to climate sciences, being jointly organized by SAMA and SPPU for capacity building of the people of South Asia and the member countries of the Non-Aligned Movement, NAM. Many of you know that we conducted the first online lecture series on atmospheric physics jointly with the SRM Institute of Science and Technology, Chennai, for 4 months during January to April 2023, in which more than 2,000 people from 48 countries registered for the course. We conducted the second online training on the WRF modeling system jointly with the CDAC, that is the Center for Development of Advanced Computing in India, during 3 to 24 April 2023 with hands-on training on supercomputing system of CDAC. We conducted the third lecture series on satellite meteorology for 20 weeks during September 2023 to February 2024. The fourth lecture series was conducted on radar meteorology jointly with the Advanced Center for Atmospheric Radar Research of Cochin University of Science and Technology from 2nd September to 3rd February 2024. It was for 20 weeks. And this is our 5th lecture series today. The syllabus of the lecture series has been designed based on the feedback and requirements of the member countries of SAMA. This lecture series is targeted at postgraduate students and professionals of non-meteorological backgrounds who are interested in learning atmospheric dynamics and its applications to climate sciences. This lecture series will continue for about 6.5 months, that is 26 weeks, from today onwards till 2nd of August 2025. As of now, about 1,075 people have registered for this course from 47 plus countries. The number is still increasing. The candidates have a wide variety of backgrounds and qualifications ranging from undergraduate, postgraduate, PhD scholars, faculties in the universities, scientists, and even some managers and administrators who are curious to learn the subject. As mentioned in the brochure, the prerequisite for this course is a good knowledge of mathematics and physics. Further, this course is a prerequisite for learning the numerical weather prediction and climate modeling and predictions. Atmospheric dynamics, or also called dynamic meteorology, is one of the fundamental subjects of MSc and MTech students of meteorology and atmospheric science in the universities and institutes. Many students find this subject as a tough subject, and very few teachers also prefer to teach this subject. However, this is one of the most important subjects and is a foundation for numerical weather prediction and climate modeling. We are fortunate to have a panel of senior scientists and professors from reputed institutions of this region who are experts in the fields. They will teach this subject with emphasis on its applications to modeling and predictions of extreme weather systems, short, medium, and long-range seasonal and climate predictions in different scenarios. They will also explain how atmospheric dynamics is important for understanding the evolution of the atmosphere and mesoscale systems like thunderstorms, cyclones, and in air pollution modeling studies, etc. As per the practice of our lecture series, certificates will be given to the participants who attend at least 75% of the lectures. Those interested in receiving certificates with grades like outstanding, excellent, very good, good, etc. will have to appear in an evaluation test at the end of the lecture series. The lectures are live streamed on the YouTube channel of SAMA. They will be available even afterwards on the YouTube for those who could not attend the course live because of the time difference between India and their countries. Our YouTube lectures get a lot of popularity because we can see the number of views keep increasing every day. We shall try to have more interactions between speakers and the participants in the lecture series. So please write your questions in the chat box. Our moderators will pick up the questions at the end of the lecture and they will be answered by the speaker. So thank you very much for listening. Enjoy and have a good day. Over to you, Dr. Rohini.
Thank you, sir. Now I request our President, SAMA, Professor Ajit Tyagi, sir, to please deliver his address.
Thank you, Dr. Rohini. And am I audible?
Yes.
Yeah.
Okay. So, very good afternoon, Honorable Vice Chancellor, Dr. Suresh Gosavi, our eminent two resource persons, the Professor Mohanty and Professor Sen. Of course, my Vice President, Dr. Kamal Chaudhary, and other members from the advisory panel, distinguished guests, and we also have our representatives from various countries attending this. So I welcome all of them. It's in fact heartening that we are able to launch this very important topic, which was in great demand, and there were a lot of requests after we have done basic atmospheric physics. Even at that time, we wanted to have a follow-up atmospheric physics followed up by the dynamics. But equally important was that two of the important topics, satellite and radar, we cover. In between, we also did a WRF modeling short course. And during that time also, it was felt that, yes, basic understanding and application of atmospheric dynamics and understanding the weather processes and use in numerical weather prediction, and even in the understanding the synoptic evolution of the systems is it's very essential that we have insight about the atmospheric dynamics. We are very fortunate that we have eminent faculty, those who have rich experience in teaching and also in practical experience in weather forecasting. So it's a good combination of our learned faculty who will be delivering these lectures. And as Professor Someshwar has given background that there have been 4 courses, each one a unique deliverables, and we got a very good feedback, and the presentations done are available as a follow-up. We are also trying to take up these as a regular practice, and this series, this particular training program is being conducted. Importance of atmospheric dynamics in the weather and climate system I don't have to highlight, but then it is essential that these are the basic governing of that atmosphere which shapes the weather systems. And through thermodynamics, through the radiation transfer, we have to have the understanding of these basic principle of atmospheric systems. And right from the genesis to the moment to the intensification and weakening, if we have to have the physical reasons behind that, then only we can really appreciate and how these are being incorporated in our weather prediction systems, whether it is synoptic or whether it is a numerical weather prediction. So this is very essential that we have a theoretical knowledge, but at the same time, the emphasis we have requested all our resource person to relate it with the operational evolution of the weather and climate, and also how do we apply them in the forecasting. So this is end-to-end. It's not just the theoretical classes, but their practical application in weather and climate system are going to be covered. So in that sense, it will fill up the gap. And we have a broad spectrum of our students who are participating, right from students to the professionals. In fact, 23% are from the working in various institutions. So they are working professionals also. We have got students, we have brought out the faculty, and of course the administrator. So it's a very good mix, and I am sure our eminent faculty will cater and target their presentations to meet this wide spectrum of our participants. So once again, let me take this opportunity to thank Pune University. Rohini and his team has done a very good job, supported by our advisory panel. Especially, I like to say Professor Bhaskar Rao, Professor Mohanty, and Dr. Datta, and other our advisory panel members who have contributed in shaping this program, and also they will be actively participating in delivering the lectures. So I'm really thankful to the Pune University and all our resource persons who will be delivering the lectures. And once again, I welcome all participants. In fact, 300 plus is a record number on the first day to have your presence in this particular webinar. So welcome and make full use of it. I wish this particular training program a great success. Thank you. Jai Hind.
Thank you very much, sir. I request our Vice President SAMA from Pakistan, Dr. Kumar Ulzam Chaudhary, to please deliver his address.
Thank you for inviting me in today's event. In fact, I am glad to know that the SAMA is organizing an online lecture series on atmospheric dynamics and its application to climate sciences jointly with the SP Pune University from January to August 2025 for capacity building of the relevant people and meteorological relevant institutions of South Asia. This is also important to know that the lectures will be delivered by very senior scientists, professors, and experts from reputed institutions of this region. Further, the syllabus of these lectures series has been designed based on the requirements of the member countries of SAMA. This is, I think, very important point. I'm also happy to know that more than 1,000 people have already registered for this course, and the number is still increasing. That's in fact indicate the credibility of this lecture series. At the end, I would like to appreciate and acknowledge the overall services and contributions of Professor Ajit Tegi, President SAMA, and Professor Dr. Das, Secretary SAMA, in its activities, as well as organizing this online weekly lecture series with jointly with SP Pune University. So I will not take much time. I am grateful for this. Thank you very much. Thank you.
Thank you very much, sir. So now we also have a video address from our Honorable Secretary, Ministry of Earth Sciences, Dr. M. Ravichandran, sir. We would like to play that video.
It is not audible.
Audio is not coming.
We redo.
Rohini,
Us-
check with the system volume.
Dr. Rohini.
Check with the system volume.
Start from the beginning and increase the system volume. Unmute it if it is unmute.
Currently, system volume is very low, but it's not only system volume. There are another. Okay, currently increase the system volume.
With maximum 100%.
Yeah, did you play before for which I suggested? Okay.
Okay.
Tested before. Yeah.
You can try at the end. Swagat, we can try at the end to play.
That also
You
will
can try in
try.
between.
Yeah, so Rohini, if it is not
Yeah, we
working,
actually tested it. But there was, we had to share this button. We actually tested it. Got again unticked. I don't know how come.
Shall I try from my end?
Yes, sir. You can try, please.
that will work better, Mustafa. Yeah.
So in that case, I will have to be given the
You are
permission to
co-host,
share
no?
my screen.
Play. Swagat can try.
Are you able to see my screen?
Yeah, it is coming, sir.
Okay, if
Screen
you are able to see my screen,
Yeah,
then
your
let me
screen is
start.
visible.
Then let me start. Oh, it should start quickly. Oh, sorry. Oh, sorry. This is, I'm clicking a wrong file. Click the wrong file. Otherwise, I will have to.
While the other talks are going on, we can do another experiment.
Yeah, I think you can try and play it at the end. Anyhow, it is
Okay,
message.
sir. Okay. Sir, click it. Yeah.
Click कर दिया. Coming up.
Yeah.
Hopefully, it's to start soon. And whatever. Slow.
No.
Yeah, it's slowly responding, very slow.
I think let us keep at the end so that.
If this is the case, then yes, sir. Yeah, I think we'll move it to the end otherwise. Something is coming.
So by that time, I'll just.
Sir, 1 second. We will try from another screen.
You try, no problem.
If you can unshare the screen, can we try from one
Okay,
more
I will stop
computer?
my sharing.
Yeah,
I will
yes.
stop sharing. I will
Yes,
stop
by
sharing.
that time, I'll switch on their camera because after that.
Yes, now it's visible, but voice still not.
Increase.
Still not.
Same thing happened actually when Rohini played.
Okay,
He is
we
visible.
will. Visible, but
He is
not
visible.
audible.
His motion is visible, but audio is not.
Yeah. Forget it otherwise.
Yeah, I think someone can try for the end.
It is a privilege to address.
Okay, it has started on my screen. Shall I share it again?
I'm getting some sound. It is my privilege. Yeah, I heard it.
Just 1 minute. Let me share the
Yeah.
screen. Share the screen. Are you able to see it?
By the
The
way,
screen
now
is-
the participants are more than 350. 331
Okay.
here, and in YouTube it is around 40.
Are you able to see
Good.
my screen?
Yeah, we can see now.
Yeah, we can see, sir.
Okay. Sharing, there is a problem. I hope it should start. Okay, let me start again.
Mhm.
Mhm. It's hanging. I think a lot of load is there, so just hanging.
I think let us.
Yeah.
It is a privilege to address
Can you hear?
this
Yeah,
Yeah,
we
sound
got
is
it.
coming. Sound is coming, sir.
Okay.
cosmic dynamics and its application to climate sciences, jointly organized by South Asian Meteorological Association, that is SAMA, and Savitribai Phule Pune University. It is indeed a very good initiative by both SAMA and Savitribai Phule University. SAMA, with its commendable efforts since 2020, has become a beacon for advancing meteorological and applied sciences throughout South Asia, fostering collaborations among 9 nations. With over 700 members and impactful initiatives, including training, workshop, webinars, and lecture series, SAMA continues to contribute significantly to capacity building and knowledge dissemination across the region in terms of meteorology and atmospheric sciences. The collaboration with the Savitribai Phule Pune University, a premier educational institution known for its excellence in atmospheric and space sciences, add immense value to this initiative. Savitri applaud SAMA and Savitribai Phule Pune University for this collaborative effort to bring together experts, students, and professionals. Such initiatives are need of the hour for this region, also critical for nurturing next generation talent and driving innovation in atmospheric sciences. I am confident this series will benefit to many and pave the way for impactful research and solutions in our collective fight against climate change. Thank you.
Okay, go ahead now. I can stop sharing.
Yeah.
Stop sharing.
Thank you, sir.
Thank you.
So
Okay,
now we will quickly have a photo session. Dr. Swagata, please take some pictures.
Oh, okay. Millie ma'am. Unshare the screen, otherwise we cannot take the photo.
Yeah, sir, please.
Share, you need to unshare your
Already
screen.
stop sharing.
Already stopped sharing, no? Oh, no.
No, it's still there.
So Someshwar has to.
Yeah, got it.
Okay, done. Is it okay? Yeah.
Yeah. Naseem Muradi ji, yeah. Hello, Dr. Abhilash.
Shanmukha sir,
Tyagi sir is not visible, yeah.
He has a problem in his camera from the beginning.
and
Karmakar sir. Yeah, Lin Wu, sir, can you switch on your camera? Yeah.
Take photo.
Karmakar sir.
Lakshmi, you take a click because it's a new system for me. So I don't know if print screen will work or not.
Print screen works.
We have taken 1 or 2, but Dr. Lakshmi can take few more.
You have taken, that's good enough.
Tyagi sir, you
He
didn't
has
come. Yeah.
problem in the camera, he's still adjusting. Everything is visible in his camera except he himself.
Ah.
Sir, you have to, sir, maybe you have to change the camera towards
He has
yourself.
flipped. He has flipped it, so we can
Yeah.
see.
Yeah.
So just rotate it towards you, or
Try to take the picture once again. Have you taken? Dr. Mohan
Yeah.
used to be expert.
Dr. Mohan, yes, he is the expert actually.
And he is not.
He is not here. Yeah, he was there, but
Yeah, he's not in his office actually.
oh, okay.
I have taken, sir.
Okay.
Good,
We have
good,
also
good.
taken. We have
I have
also
Okay,
taken two
very
clips.
good.
Yeah,
So,
yeah.
Yeah.
Dr. Rohini, have you taken the second page also? I mean, it's 2 + 2 as to 2. So 1, 2, 2, 2.
Yes, sir. I have
Okay,
taken
fine. Thank
both.
you.
Yeah.
Okay, fine. Thank you. So with the permission of the Professor Mohanty, can I leave because I have another meeting to do? Thank you.
oh, sure.
Thank you, sir.
Thank you. Yeah.
So now I would like to request Dr. Swagata Paira Bit Mesra to please introduce our first speaker, Professor U.C. Mohanty sir, who is former Professor IIT Delhi and IIT Bhubneswar and now as a distinguished Professor CCSA SOA.
Thank you, Rohini. So will you share the file or?
Yes, I will share the file for you.
Okay. Thank you, Rohini. So it's really my privilege to introduce Mohanty sir. I mean, I'm quite lucky that I was direct student of him at IIT Delhi. Mohanty sir worked around 33 years at IIT Delhi in various capacities from lecturer to head and professor. Also, he served in IIT Bhubneswar for 9 years as a visiting professor in the School of Earth, Ocean and Climate Sciences. Currently, he is serving as a distinguished professor in the Center for Climate Smart Agriculture of Shiksha O Anusandhan, deemed to be University, Bhubaneswar. He also served the DST NCM RWF for more than 2 years as head of the research. Under his guidance, medium range weather forecasting system was for the first time operational in the country in June 1994. He was in honorary capacity served the Odisha Vigyan Academy as its president from 2013 to 2015. He had also served as vice president of Indian Meteorological Society and senior associate of International Center for Theoretical Physics, ICTP, which is Italy. Mohanty sir is recognized for his deep understanding of fundamental atmospheric science, observational studies, and numerical modeling. His outstanding researches lead to set up several milestones, especially in the prediction of weather and climate, that have widely been recognized by the scientific communities worldwide. The principal facet of his work and research achievement include prediction of high impact extreme weather events such as tropical cyclones and associated storm surges, understanding and prediction of summer monsoon process, including heavy rainfall events, monsoon circulation, and associated monsoon disturbances, severe thunderstorm and location specific extreme weather events over India. Rohini, should you go for the next slide or I? His research was also involved monthly and seasonal scale prediction of precipitation and air temperature at the surface and application of the same for climate risk management in the sector of agriculture. Some of his and his team research work are transferred to IMD and Meteorological Directorate of Indian Air Force for their operational uses. His illustrious teaching and research career spans over 48 years, with more than 50, during which he has published a number of papers in professional, national and international journals of repute, besides contributing 70 published work as a technical reports and several book chapters. Again, there is a staggering number under his able guidance. So far, 44 have been awarded PhD degree and 3 have been continuing their research for PhD degree from IIT Bhubneswar and SOA deemed to be University of Bhubneswar. He has achieved a lot of honors and awards. One of the best ones, Shanti Sharu Bhatnagar Prize, National Award in Atmospheric Sciences and Technology, Biju Patnaik Award for Scientific Excellence, Sir Gilbert Walker Gold Medal. Also, he is a fellow of Indian National Science Academy, Indian Academy of Science, National Academy of Sciences, Indian National Academy of Engineering. Also, he has received in 2018 Odisha Citizen Award. There are many more, but quickly, he has a publication of more around 250, total 237, international 151, and national 87. PhD, okay, this is already updated with the 44. He has done his PhD in 1978 from Russia, Odisha Hydrometeorological Institute. Welcome, sir. I'm very happy that I could be able to introduce you. So now the floor is yours.
Thank you very much, Dr. Swagat. At the outset, very good afternoon to Professor Suresh Gosari, the Vice Chancellor of the Pune University, Professor Dr. Ajit Tyagi, Air Vice Marshal, President of the SAMA, Professor Somisha Das, Secretary, Dr. Chaudhary, Vice President, Dr. Karmakar, and many more my friends and colleagues. Very good afternoon and Happy New Year to all of you in person, because now I will start my lecture. So I have to run switch over to PPT mode. Where I have to share, it is green.
Sir, there is a green button down which says
yes, share. Okay. Share has one some dynamic made presentation. Yeah. How do you from? So I have to go to beginning actually, because it is end. I need help from.
sir, you can just
okay. Yeah, I have come now.
Sir, press F5 directly. It will.
Yeah,
okay. But not require full screen.
Yeah, F5.
F5. Here.
Sir, or you can press this cup button on the right corner.
Okay, full screen.
After your Gmail, you see
that one, yeah.
Yeah, this one.
Okay.
Yes, yes.
Now it is visible.
Yes.
Yeah.
Now it is audible also.
Yes.
Yes.
Okay, so very good afternoon all to our participants, besides our esteemed dignitaries for the inauguration function. So it is, I thank to SAMA to give me this privilege to give the opening lecture. And it is an introductory lecture on atmospheric dynamics and its application to climate science, the theme of this series. So outline of my introductory lecture involves basic variables representing the atmosphere, types of forces in the atmosphere, global wind circulation, mathematical representation of atmospheric processes, dynamical framework for the modeling. And this modeling is for short, medium, and mid-scale. And in fact, as you know, with climate change, the weather and climate science plays very, very important role in all sectors. And I was so overwhelmed that IMD celebrated completion of 150 years, and they have a quiz for the children of the 8th, 9th, and 11th class, and all over the country, and even students from Northeast, students from different sectors of the country also participated and awarded. So this shows that the interest of everybody in this science, because this is science for the common people, and it is needed for everyone. But we have already, our first lecture was physics of the atmosphere, and it will be incomplete if we don't have dynamics of the atmosphere, though it is a little difficult. But my lecture is really very simple, so all of you can easily understand, because it is an introductory lecture. So if you see components of the Earth atmosphere, so this is a globe. I took a column, and in the column, if you see that we have two types of things, that basic variables for atmosphere. One is the motion, another is the mass. And this mass, it is actually that it deals with the physics of the atmosphere. That is the pressure, temperature, specific humidity, air density, and so on. So I will not dwell on that to keep this time. I will come to part motion of the atmosphere, wind velocity vectors. Here actually this being wind is not a scalar quantity like other variables of mass. So this wind is a vector variable, because as you know, actually we have zonal wind we call in, and that is U component. And in the meteorology or atmosphere science, we tell from where the things are blowing, not where it is going. Because you know that Cartesian coordinate x, y, z, it starts from origin and goes the way it moves. But in the atmosphere, if we call easterly wind, that means it is coming from east to west, and that is what we call zonal wind. Similarly, north and south, the motion that we call meridional wind, that is B component. And vertical component, upward motion, that is the W component. So these are the three components of the variables. And out of that, generally, most of the time we measure only zonal and meridional component of the wind. And you know, atmosphere science or climate science is science with initial value problem. Without knowing initial condition, we cannot move further. So therefore, it is observation is the backbone. And as you know, in atmosphere science, we always use the most sophisticated equipment that are available in the world to use it for atmosphere science. So also, it is science of the different scales, starting from very small turbulent scale to that of the whole planet Earth. Therefore, we always like as finer as possible. So therefore, always our science use the best possible computer in the world for the atmosphere science or climate science. So this is a science of science and technology, and many places it is used as a technology, many places it was a science, but this is a fundamentally a application of various science in the engineering, and finally lead to the understanding and prediction of our planet, atmosphere of our planet Earth. So I start with a very simple pattern. Can we touch the wind? I'll close this one, the side one. Rohini, can you tell me how I'll close this part? I don't want, because
sir, there is a 3 buttons on the top. If you will just minimize it, it will minimize.
Okay,
yeah.
Okay, great. So actually, the first question comes, searching the wind. Actually, this is a cartoon I am showing you. We all know wind is alive. Every time, everywhere, every moment, we are touched with the wind in our respiration system to our surrounding. But have anybody touched the wind or searched the wind? So this cartoon shows in the 14th century, this man, he saw that backward of his garden, the trees are bending and falling and breaking. So he searched for the ghost. That is, who is actually doing this thing? I cannot see anybody, but how many trees broken? So that is what it started. We all are searching the wind. Till now also, we are searching the wind. We cannot see the wind. We can feel it. And with the models and with the equations we will present today in brief, and it will be extended in lectures, we can actually formulate laws for the wind and how it moved and how it changed and how it changed our weather and climate. The central goal of atmospheric science is to learn about the winds, to understand why they come to life, why they take the forms and patterns they do, why they change and evolve, and finally die in the birth of new winds. So as you know, wind is starts with the scale of turbulence with a few centimeters to the jet streams which covers the entire globe. So can you imagine from few centimeters to entire globe? And wind is generated always with the turbulence, and also it die with the turbulence. But it has several applications almost in all fields. Knowledge about wind contributes to the theory of atmospheric motion. Through this theory is a human creation. Though this theory is a human creation, I believe it mirrors nature's plan for the winds. With it, we can reach for and perhaps even touch some of the wind's own truth. That means we see that cyclonic wind, anticyclonic wind, clockwise, anti-clockwise, and so on. So all these things you can visualize, you can simulate, you can animate, but you cannot touch. This is a picture from satellite. Atmospheric dynamics combines thermodynamics of heat and energy transfer and mechanics of motion to produce a theory of thermally forced motion on a rotating planet Earth, that is the winds. And the atmospheric modeling or atmospheric understanding of dynamics and physics, they are based on the laws of physics. They are very fundamental, which is now taught in the school level also. And for the wind or the motion, we use the conservation of momentum, that is Newton's second law, that you all know familiar, laws of conservation of momentum. Conservation of mass, continuity equation, that gives the pressure. Conservation of energy, that main energy, the Earth's major source of energy, the solar energy, and then how it is transmitted through and scattered, reflected, and so on. So that is thermodynamics, that is temperature. Similarly, conservation of water vapor. Our planet, we are lucky that we have the water, and we call life is the water, and we have the water, and that is measured in various ways, and we call mainly humidity, relative humidity, specific humidity, and so on. And after all, the air, which is a combination of several gases, mainly nitrogen and oxygen and many trace gases, this is behave like a perfect gas law. So this is combination of Boyle's law and Sells law and combined gas. So here today, we are considering only top one, that is conservation of momentum. You see that when wind is blowing, that means it generates the kinetic energy. Any motion, it gives the kinetic energy. So energy means it needs some source which will drive that. The types of forces that we encounter in the atmosphere are broadly of the following. One is the dynamical forces, other is the physical forces. Physical forces we dealt very thoroughly in the physics of the atmosphere, except the momentum flux. And dynamics actually, we have two types of motions and forces. One is the fundamental force or major force, they are the pressure gradient force. So that the pressure gradient force, which you call the body force, that causes the motion, like if you have water up 2 levels and you will leave it freely, then water from higher level, it will go to lower level till it becomes equal. It doesn't need any other thing. Same way, pressure gradient, we have high pressures and low pressure. And in the atmosphere, there is no connectivity required because the whole atmosphere is continuous. So therefore, wind blows from high pressure to low pressure, and that gives the wind. Another thing actually that air has a mass and Earth is a bigger body. So we have a gravitational force. Then we are dealing with different media. One is the atmosphere, one is the land, one is the ocean. They are not of same density. So there is a strong gradient of density. So when there is a gradient of any of these 7 variables, it gives the friction. So friction force is one of the important force. In fact, actually, as you know, if there is no friction, we cannot walk. If you go to snow surface, it is very difficult to walk because it is less friction. And you have seen that cosmos, and when people are going the satellite, they just float because there is no friction. But friction is very, very important for our walking. Same way, in the atmosphere, as we tell, everything starts with the eddies, that is the frictions. and that carries the energy from the Earth's surface to the atmosphere. And when the wind is more, then it tries to stop it. That means by friction, then wind also dissipates. So it is a creator and a destroyer of the wind in the atmosphere. So friction is very, very important. And it is also day-to-day life, the transport of the pollutants and many other activities in the lower atmosphere. Also, it is governed by the frictional forces. And that will be learned that forces. So these are the fundamental forces in the atmosphere which give our thermodynamics of the meteorology, that pressure gradient, gravitation, and frictional forces. In addition to that, you know, our Earth is rotating. In a rotating ball, like you take a ball and take water, which you can see, if you rotate that ball, then you can see that the flow is deflected. So in the atmosphere, we call it apparent force because generally force gives the motion. But here, the motion gives these forces. Now, it is the just opposite way. That is, it's not that a Coriolis force is generating in the atmosphere, but it is the motion in a rotating frame. It gives a deflective force, which is the Coriolis. Similarly, the centripetal force and centrifugal force, they arises due to different type of curved type of motion, because in the atmosphere we don't get always straight line motion. It is, we have cyclonic wind in the northern hemisphere, you know that it is circular anti-clockwise motions, and anticyclone, it is a high pressure zone, we have a clockwise motion. So these things, like you go in a bicycle, you go straight line, if a circle comes, then you have to bend yourself so that you can retain yourself. You go straight, then you will go out of the track. Same way, wind, they have to be in the track with the centripetal and centrifugal forces. And these forces, we call them the apparent forces because the motion itself gives this force in a rotating or Earth's atmosphere. And third, equally important force is the physical forces. Here, actually, I will deal with only momentum flux, which is arises due to motions, and besides that, central heat flux, moisture flux, radiation, and so on. That is already we have dealt in the physics of the atmosphere. The basic mechanism of weather results from the temperature difference from one place to another place. Because if you tell which is the origin, whether wind is the past or temperature is the past, then you know that temperature is the past. Here actually no chicken and egg problem, and it is the egg is the temperature. So all the weather process starts with the temperature. On large scales, temperature differences occurs because the place which are closer to equator or closer to sun, they receive more energy per unit area from sun than the regions closer to the poles. So therefore, we have a temperature gradient because of the solar energy we are receiving over the Earth's surface that you have learned in the physics of the atmosphere. So the equatorial belt or equatorial region, whether it is atmosphere or ocean, they get more energy, and in the polar region, they get less. So we have a north-south temperature gradient built up. In addition, on local scales, temperature differences can occur because of different surfaces. Oceans, forests, ice sheets, deserts, or man-made objects, like your urbanization and so on, have different physical characteristics such as the reflectivity, roughness, or moisture content. So due to that, we get also variation. Like a desert, it warm up much faster and cool down much faster. But whereas ocean, we call the reservoir of energy because it is warm up very slowly, but cool down also very slowly. In a desert, the day to night temperature can be as high as 15, 20, 25 degrees. But ocean, it may be hardly 1 degree, unless there is some system for tropical cycle. So therefore, these temperature gradients creates by both surface process local as well as the global, that is north-south temperature gradient. Surface temperature difference in turn causes pressure difference. Because if the air is hot, you know that hot means it expands the air. So that means the density will decrease. because we know the equation of state, P by rho or P into alpha is equal to RT. R is a constant, universal gas constant. So P alpha T and pressure and temperature, they are directly related. So that means if a warmer temperature, then it will be low pressure. If a colder air, that temperature is low, this is a high pressure. So we create this high pressure, low pressure, which is the start of our force in the atmosphere for the motion that is comes due to temperature gradient. Above it, and there are air expands and lower in the air temperature and so on. The resulting horizontal pressure gradients that accelerate the air from high pressure region to low pressure region, creating the wind. So therefore, wind is created initially due to the pressure gradient force. Pressure gradient force comes due to temperature. And temperature comes, as I have explained you, and all source is the sun. Earth's rotation then causes the curvature of the flow. That is the first is the Coriolis force, and Coriolis effect of Coriolis force, and you will learn about that more details as we will go on further. Smaller scale examples is the coastal bridge. The stronger temperature contrast between place cold and tropical air is right to the jet stream. So you know the familiar jet stream, which covers the entire globe as a wave around the entire globe. Most weather systems in the middle latitudes caused by the instability of the jet. Weather systems in the tropics are caused by different processes such as monsoons or organic thunderstorms, tropical cyclones, and so on. So this is the very basics of the motion in the atmosphere, and knowledge about the motion of the atmosphere is the dynamics of the atmosphere. Dynamic meteorology mainly covers the motion of the atmosphere in our planet Earth. And for this, equality is there, mathematics, obviously, partial differential equations, and then, of course, the vector algebra is very much essential. Because wind, as you know, that is U, V, W, they have a direction and magnitude, and therefore vector algebra is required, and that is also covered in your course, vector algebra first, because two major things in the atmosphere is the convergence, divergence, and rotation, vorticity. And vorticity and divergence, they come from the curl of the wind that gives you vorticity, grad of the wind that gives divergence. Therefore, it is always required, but I will not cover this because in my small lecture of 45 minutes. So whole basic motion of the atmosphere that I gave you first is schematic. The top one you see that the wind is converging low level. We have the water vapors or water, and then that evaporates, it goes up, it cools down from the cloud, and upper level it will divert. And that is what we call the conservation mass, that is Dyne's compensation rule, that is if one level is a convergence, upper level is need to be divergent so that the mass is balanced there. And that creates a low level cyclonic wind or low level low pressure, high level high pressure, and that build up really the motion in the atmosphere. And as I told you, this convergence, divergence, and vorticity, are the major things, and most of the forecasts done by synoptic method or understanding, it comes in the convergence, divergence, or vorticity. It may be cyclonic motion, it is anticyclonic motion, it may be trough, it may be reach, it as I told, it will air will converge or air will diverge. So all the air motions goes with these parameters, and there, as I told you, vorticity, the curl of the horizontal wind, and grad of the horizontal wind, your divergence and convergence. Similarly, as I told you, sea and land breeze, there are two examples that how the temperature lead to the motions. In the daytime, land is warm up, ocean remain cooler. The warm up means low pressure is generated over the land, and air will try to blow from the high pressure from the ocean to the land. In the night time, land is cooled down, and land actually memory is very short. As I told deserts, it has no water vapor. then it is much more shorter memory. So therefore, land is cooled down faster, but still ocean even warmer. So therefore, night time, the low pressure will be on the warm air that is over the ocean, and cold air will be over the land. So therefore, the breeze will come from the low pressure to from high pressure to that of the low pressure. So therefore, you get circulations, land sea breeze, and land breeze. So this is again, you see that it's a contrast of the temperature over the two different medias, because as I told, two contrasts is one is the ocean, one is the deserts or land, simple land, no vegetation or nothing. Therefore, that gives the two contrasts, warm and cold, and that gives the motion. Similarly, the thunderstorm, the atmosphere, which is very well-known phenomena, and most of you know that we have the severe thunderstorms, lightning, and so on. Again, that if you see, that again comes with the same process. When the land is heated up, then our air is converted there, and then low pressure, then air is coming to moisture, then it build up from the clouds, and cloud can go to deep levels, and we can severe thunderstorm, which is cumulonimbus cloud, and then when it is water is became frozen up, as it rises up, and then it is from water to again it may be the solid stage of ice, and in our atmosphere we get water in all its three phases: vapor, gaseous stage, water, liquid stage, and ice stage. All the three phases that we all are familiar with physics, that is what is there. Then once the mass is increases with the formation of ice, then it is heavier and it comes down, and we have downdraft, and then we get the rainfall and precipitation and so on. So all this mechanism comes due to the motion, but the motion is really initiated with the redistribution of the mass, that is the pressure, and pressure is coming due to temperature. So that is always you have to remember that is the process going on. Similar are monsoon, which is actually very familiar to many of our participants who are from SAMA regions or nearby regions. You know that we have very stable circulation process in the atmosphere, that the monsoon system, which gives almost 70 to 75% rainfall over the Indian subcontinent, like Bangladesh, Nepal, Bhutan, Pakistan, India, and Myanmar, and Sri Lanka, and so on. So here actually, again, we have the motion, low level, we have south westerly wind, which call also southwest monsoon, and then upper level, then when this converges over the land, then rises up, and then it forms the high pressure at the upper level, that is Tibetan high, and tropical easterly that is formed at the level of 150 level, where the wind is diverging from the region and facilitating the acceleration, the low level convergence over the Indian subcontinent. So monsoon is a very good example of the formally driven, how the temperature that drives the motion, and the entire semi-permanent feature of monsoon exists almost 4 months in this part of the world. So many semi-permanent features and so on. But again, I will not take time for that because that is a separate topic. But this all I am showing you, these three things, starting from the land sea breeze to that of severe thunderstorm to that of the monsoon, all have the same basic principle. That is the heating of the atmosphere, giving the low pressures and making a dense compensation in the column and giving our low level convergence, upper level divergence. Same way also tropical cyclone. So I will not go too further in that direction. So if it's a global wind circulation, so wind actually a very major thing, and as we know, as I told, from our respiration system to grow, it is all is the wind actually. And they have also semi-permanent features are there. We have subtropical high, IIT is the intertropical convergence zone, that is low pressure zone, close to equator, and having a little bit of movement from south to north as we move in the time. And then we get two winds that go from northern hemisphere, from the subtropical high of the northern hemisphere to the equator region, we get northeast winds, and similarly from south subtropics to that of the equator side to ITCD, we get also southeasterly wind, and they are known as the trade winds. Why it is called trade winds? As you know, because most of the trade in the past, when we are not knowing the industrial revolution was not there, go thousands of years back, people are doing their navigations. They are doing communicating each country with other countries, with their goods, with their passengers, and so on, through only the ocean. And that time, they are taking the boats and seeing the motion of the wind, which are almost semi-permanent features, and they are navigating from one country or one continent to other continent. That is how people move from Europe to Asia countries, or Europe to American continents, and so on. So this is all done in this trade zone, that is subtropics of the northern to subtropical southern hemisphere, having semi-permanent features and so on. Similarly, we have the polar regions, and you have Australis, and these Australis, they form the Australis there. And we have also some, and this circulation, north-south circulation, we call it the Hadley cell, and east-west circulation cells, they are known as parallel cells. And we have also polar region, polar cells, and polar easterly and westerly. So these are the really broad scale motions in the atmosphere. They are semi-permanent features. And this is also given here, general circulation of the atmosphere, that is very familiar to most of you, that low pressure, that is the ITCD region. Then you have a high pressure, subtropical high pressure region, where we form the jet streams, and we have the polar easterlies, and then westerlies in the polar easterly to that of the high pressure, and high pressure to equatorial region, we have trade wind regions. So this is very, very familiar motions in the atmosphere, and this motions gives you the polar jets, subtropical jet, that is westerly jets, trade winds, ITCD, monsoon, and so on. So I touch it very short way, but this is actually what is the observed motion in the atmosphere. And without knowing that, we cannot know the climate. Because the wind, the temperature, which actually I am telling that is the root start, but then temperature is mainly, most of the things in the atmosphere, they are affected by the wind. The advection mechanism, as I will go further, I will show you that if you go to form a model, advection is the major thing which play a role to advect the temperature, advect the moisture, and so on, even advect the mass momentum. The principles of weather and climate systems, they are the energy sources like radiation, as I told, which give the temperature. The forces, that is dynamics and physics. Atmospheric motion is most fundamental, that as we are discussing now. And mass of the atmosphere is pressure, and pressure is governed by the temperature, humidity. And another most important thing, the hydrological cycle, it is covered already in the physics of the atmosphere. Because we are lucky, most of our weather and climate, there comes due to water. Though actually, the water that we get in the planet or our use is less than 1%. Because 97% of water are available in the oceans, which is covered 2/3 of the region, and also polar ice and so on. But only less than 1% we get over the land. That is the fresh water. And out of that, most of the water also in the underground, we get a fraction of the percent. That is the fresh water, which comes in the form of precipitation, that is either rainfall or snowfall. And these things, actually, as you know, water is the life. So therefore, water cycle is also very important. And this water cycle also driven by the winds in the atmosphere. So now I'll come to little. So this is the pure fundamental things I have told you. Now I'm coming a little bit, of course, not very top subject, because as you move in the dynamics of the atmosphere, you will see the key vector algebra and so on, partial differential equations, then equational form, mathematical form of these things. But I'll give you little basics of mathematical representation of the atmospheric processes. That is dynamical frame of. We told that 7 variables is there, and the behavior of these 7 variables is governed by the 7 equations, because as you know, these 7 variables, they have value with space and time. So that's why you call it a 4-dimensional fields. And these 7 variables are the dependent variables, because they vary from in space and time, from place to place, from height to height, and from time to time. So they are the dependent variables. Whereas your x, y, z, of course, we replace the z with pressure coordinate or temperature coordinate and so on. Then time is one of the factors. Here of these 7 variables is governed by the 7 equations, because these dependent variables, if you want to determine them properly, then you need the same number of equations at least. So we have 7 equations. They are formed from classical physics, hydrodynamics and thermodynamics. Hydrodynamic equations, that is 3 equations of motion, that U, V, and W components. These components comes from the Newton's second law. Force is equal mass into acceleration in 3 directions, x, y, z. Another force is the gravity or gravitational attraction of the Earth, and centrifugal forces that I have told you. And pressure gradient force, that also we have discussed earlier. Coriolis force, as I told you, it is the apparent deflecting force. It does not change the motion. It is change the direction of the motion. So also centripetal and centrifugal force. They arise due to the motion, and they don't change the motion or magnitude of, but they give the direction. But maximum change in the magnitude, that comes play due to the friction or turbulence. The friction, as I told you, the land surface has a different density of the soils, the different density of the water, to density of the air. So therefore, when the gradient, strong gradient takes place, then turbulence takes place. And the friction job is, as I told you, it tries to reduce the motion. It does not allow, because that is what happens when you start running, and you know that you cannot run to the extent because friction is there. So this friction starts from the molecular frictions, that of the eddy frictions, and this area also starts with few centimeters to a very large scale area also. So therefore, if you see the equation for the motion in the atmosphere, that is the dynamics of the atmosphere, we call, that is V is here, V vector, dV by dt, the total change of velocity with the time is equal to sum of the forces per unit mass. And that is only this line of equation that give you your entire dynamic method. Then we have the equation of continuity, law of conservation of air mass, because density, as you know that key. And then actually, what we do actually for our simplicity, but actually density not a constant. It varies with the time and space. But for our simplicity, we assume the air is incompressible fluid. Because if we don't allow that incompressibility, then we will allow the sound wave in the atmosphere. That is compression and rarefication, where density can be more and less. That will give you compression or rarefication and propagation of the sound wave. Then sound wave is existing in the atmosphere. That's why I'm talking and you are hearing. And if not so, it is incompressible like a wall, then you cannot hear me. Therefore, it is compressible. For our simplicity, no weather or climate change system will change with the sound. If all of us shout It will not change any temperature or any wind or any weather systems. That's why, for our simplicity of our equations to solve numerically as we go further, we assume the atmosphere is incompressible. Other the thermodynamic equations, and now I'll skip that one because that you have already dealt, and those who have learned only physical meteorology, you have already learned that. So let us not spend time for that. And similar, the moisture, it came as will play, and it is also taught in the physics of the atmosphere. Those who have not attended the physics of the atmosphere, as Professor Samisa Das told, these all are available in the YouTube, and you can go and see and refresh yourself. And if you have any queries anytime, you are already free to access. Anything somebody tell you?
No, sir, you please continue. Yeah.
And similarly, that moisture actually, which is very, very important for our atmosphere, as I told you, the water, the light, and that is governed again by evaporation and precipitation. Evaporation is the source, and precipitation is the sink in the atmosphere. And with all, we have the diffusion. It is vertical and horizontal, but most important, the vertical diffusion. So d over dt, dq by dt, q is the specific unit. So I will not go to that because it is already dealt. So the equation of motion, if you write, so we have three components. One is that component is your zonal component, du by dt, total derivative, is equal to pressure gradient plus Coriolis force plus turbulence force, frictional force. That is the zonal component. Similarly, meridional component, total derivative of the wind, dv by dt, d is the meridional wind. That is again pressure gradient of the in the meridian direction, and then we have the Coriolis force, and then friction. Then third equation, which is the vertical motion, that I am not putting in the total because, as you know, in the atmosphere, very rare case with very specific equipments, we measure the vertical velocity only at the limited places for our understanding. But in the atmosphere, vertical wind is very, very important role. In fact, you are all vertical motions which leads to the clouds and no clouds, or descending motion and ascending motion and so on. It is all driven by the vertical velocity. But in the atmosphere, we have a very stable assumption, which we call vertical component equation of the motion. For large scale wind, we call it the hydrostatic assumption. And this is also very fundamental things in the dynamic meteorology. All have to know that hydrostatic assumptions, because your motion may be a mesoscale motion with non-hydrostatic, or it is hydrostatic. But in the measure of the large scale motion, they are hydrostatic, where the vertical component of wind acceleration is much smaller in few orders compared to our vertical pressure gradient, which is quite large, and minus d rho, that is gravitation. So therefore, these two components are of one order, whereas d dt, if you make a scale and say about 10 power minus 7 or so, whereas the 10 power 1 is a dp by dz or minus 0. So therefore, what we do in the atmosphere, we assume the hydrostatic assumption. That makes our life simpler because vertical wind, generally we don't measure. There's a good balance between the vertical pressure gradient, which is always act upward, because as you move up, your pressure decreases. So high pressure is the lower atmosphere, and as you go up and up, your pressure decreases. So it is act upward, dp by dz. Whereas the gravity, it is always act downward, and it depends upon the mass into acceleration. This is the acceleration due to gravity, and rho is the mass, so it will act towards the earth, so downward. The upward pressure gradient balanced by very nicely by the downward gravitational forces, and that is what we call a hydrostatic assumption. But remember, the vertical wind is not zero. Because if you make vertical only 0, then that comes entirely different thing, and you will not get many physics of the atmosphere if you make W is 0. But dW by dt is actually very small compared to these two components. Then the mass continuity equation, again, as I told, we take incompressible fluid for the eliminating sound waves, and then it gives us du by dx, dv by dy plus dw by dz equals 0. And the equation of state, you all know, P alpha is equal to RT or P by rho is equal to RT. And the thermodynamic equation, I will not deal with it, is done earlier. So the total derivative, which I am showing all the places d by dt, that is the partial derivative, that d by dt plus u d by dx plus d by dy plus w d by dz. That u d by dx, v d by dy, w d by dz, these are the advection terms. All your fields, all your mass fields, they are advected. Even the momentum is advected. So therefore, actually, total derivative, we have to change it to partial derivative. So that's why we learn partial differential equations to solve these equations. And also we learn the vector things because U, V, W, they are components of the vector V. So 7 equations now we have with the 7 variables. So the system is closed, and then these form the general equations for a complete atmospheric modeling or understanding the atmosphere, whether it is a very short nowcasting to very large climate or climate change, the equation broadly are same. So this is all the equations. And sometimes, many times in global models, instead of U and V, we take vorticity divergence, because there became convert the vector things to scalar, because it has direction. But what will direction the pole? What is the zonal wind at pole at singular point? And what is the meridional wind? So therefore, many of the spherical global models, it is coordinate system, not, we don't go the Cartesian coordinate x, y, and we go to polar coordinate systems, because we are on a spherical or oblique earth. And these equations are dealt, and at this stage, we have taken a large number of assumptions also. One is the hydrostatic balance, we have told you recently. Neglect of the molecular diffusion. Atmosphere, dry air, and water vapor both behave as a perfect gas. Volume occupied liquid water and ice neglected compared with the volume occupied dry air and water vapor, because dry air is much larger, where the water and ice and so on, they are very, very small fraction. That I told you, that is less than 1%, and even a fractional point. Neglect of storage of liquid water or ice in the model, because we tell that what is condensed, it is falling down. It may be re-evaporate, but it falls down. Neglect of the density change due to evaporation or precipitation. Then when you go to the complex system and we want to know whether, and now I will switch over to a little bit, perhaps my time is coming to close to end, so I will switch over that if you want a really model, or even you want to, even classical way of knowing the weather and climate, then it needs 4 pillars, 4 circles that are interdependent. Weather and climate science, the observational science, it starts with observation. The observations gives us an understanding. And understanding can give us to a model. And once you have a model, we can go for an objective way of prediction. And now, anything we are doing, weather and climate prediction, it is generally done by the numerical models, and the modeling gives us the prediction. Therefore, observations, understanding, modeling, and prediction are interrelated and correlated. And that gives the entire concept. Then actually, if you see the science of weather science or climate science, it covers all branches that we are acquainted with so far. The physical science, the physics, that are very, very important. It gives the atmospheric motion, it gives the atmospheric thermodynamics, it gives the physical processes like radiation, turbulence, convection, and so on. It all comes as the physics. Mathematical science is very, very important because you cannot solve these nonlinear partial differential equations without mathematics. The mathematical science, it gives the numerical analysis, partial differential equations, fluid dynamics, vector analysis, and so on. So we get that equations of these processes only formulated with mathematical equations so that you can go for the modeling. But then our atmosphere is not isolated from the chemical processes. We have the atmospheric chemistry, composition of the atmosphere, aerosol and greenhouse gases in the atmosphere. And you know that if we write down each equation of the chemical equation in the atmosphere, the number is around 2,000. Because in the atmosphere, we have the aerosols, like sulfate and so on, and carbon, black carbon and so on. We have the water and we have the energy. So what you need a chemical lab? You need a salt or chemical things that we have, aerosol. We have the water and we have the energy, solar energy. So you get many interactions in the atmosphere. Again, as we move more complex atmospheric models to understand the weather and climate, we have to go the chemistry of the atmosphere or chemical sciences. No way less important is the biological science. Because many times we feel that atmospheric science is all mathematics and physics. No, it has a lot of parts on the biological science. Because all our biological things survive with the atmosphere. Can you tell me any food you can get without water? Water is the most important ingredient. So atmosphere influences all our food production, food security. But at the same time, the biosphere plays a very important role in our maintaining the atmosphere. So here in the biosphere, we have evapotranspiration. Water which we are getting, which is going to root zone, which is infiltrating the atmosphere, ground, they come back with the root zone, with the evapotranspiration, osmosis process, and then evaporate from the plant, leaves. The land use, land cover, the albedo, it is changed depending on the type of the vegetation. Roughness, which actually again dissipated wind, that comes also with the trees and plants and so on. That's why in the coastal area, we plant the trees so that when cyclone coming with the vigorous wind, it can dissipate with that type of plants so that the animal or life of human being and animals, they are less affected by planting the trees around the coastal lines so that actually it can dissipate the roughness. And also it is change the albedo, the heat balance in the atmosphere. So biosphere plays very, very important role, as important the atmosphere plays on the biological. Desertification and climate change and so on. Similarly, the lithosphere, cryosphere, soil characteristics, surface and subsurface soils and hydrology, that earth science also plays a very important role. You know that the role of the cryosphere in our atmospheric energy balance, and you know that volcanic eruptions and so on. So they play also very important role in our atmospheric science, which gives us weather climate. Similarly, environmental science, air pollution, water pollution, ecosystems, clean energy, all these things again associated with our atmosphere and environmental science. Overall, all even present day. We cannot run these models because they are not linear, they are non-linear partial differential equation. Without making a computer, we cannot solve it. In fact, first numerical multiplication started in 1950s when we have a first computer there in 1948. It was new. Since then, if we see the history of the computers and the weather prediction, skill of the weather and climate models, it all depend upon the power of the computer we have. We started with small computers, and now we have come to petaflops and so on. The more we have, the more we need. And if you see always the fastest computer it comes to the atmospheric science, because we want to go to the scale of centimeter, which is not possible. So observations and modeling, all these things need extensively the computational methods, data mining, artificial intelligence, machine learning, parallel processing, architecture programming, all these things of computer science are extensively used in the weather and climate sciences. So without that, I don't know how the people are moving. And without that, with a calculator, when Richardson started his first weather prediction model, it was a failure. And then we call that the primitive equation is generated there. That time he failed because we are not knowing the CFL criteria of mathematics, that it should be stable solution to be there. And for that, what is the relation with the space and time required? And these aspects were actually composed of the waves, and therefore we need all these branches. So you see almost all branches of science and engineering. And of course, I'm not showing you the observation part. In observation, as I told you, when aircraft came, when satellite came, when radar system came, and all these things, any new advancement in equipments used for the atmosphere science, because 2/3 of our area is the data sparse region, like oceans, polar regions, mountains, and deserts, where it is very difficult to take observations. We get hardly 20% area where human beings are living, and they can take observations. Most of the observations we get by remote sensing.
Sir, 2 minutes more.
Yeah, my time is coming to close. So I think I will close soon. So if you see the atmosphere as a climate system, it has actually a climate system. It has actually 1, 2, 3, 4, 5, 6 spheres: lithosphere, cryosphere, hydrosphere, biosphere, atmosphere, and outer space, that is solar space. So this is a science that no boundary. Like horizontally, there is no boundary. Similarly, vertically, there is no boundary. It is boundless. But they have also interaction, but different scales. Anyhow, this is the climate science. So I will not spend time because my time comes to close. And weather system is a highly nonlinear coupled system. The components of the weather system are open and non-isolated subsystems. They interact on a wide range of space and time. They are strongly coupled and are characterized by intense interaction at various time scales. So this is a schematic way of the model that is generally used. And this is where your wind, temperature, humidity, they are basic parameters. They are majorly done by the adiabatic process, that is your mainly the advection mechanism, that is, and then governed by number of physical processes. So these are the physical processes in the atmosphere. Again, I will not spend time. It was taught in the physics of the atmosphere. Simple plant, how much is the role that I have told you, that even a single plant, it is governed our atmosphere by radiative balance, water balance, and turbulent fluxes. So this is a type of motion in the, I will not go there. And here, I think I try to complete my short lecture in allocated time. Thank you very much for your kind attention to hear my lecture.
Thank you very much, sir. So we will take the questions after the second lecture together.
Sure.
So now I request, sir, if you can unshare the screen.
Yeah, sure. Where it is, how I want to share.
Maybe on the top you will have a...
Stop share.
Stop share.
Right.
I request Dr. Milli Ghoshni Lala from BIT Mesra to please introduce our second speaker, Dr. P.N. Sen, who was Deputy Director General retired from IMD and now is a visiting faculty in Department of Atmospheric and Space Sciences, SPPU.
Thank you, ma'am. Please share the screen. Thank you. It's my pleasure to introduce Dr. P.N. Sen. Dr. P.N. Sen joined the India Meteorological Department in 1971 and worked in different capacities at DDGM, CNG, DDGM, WF, and at various centers, including MC Guwahati and RMC Kolkata. After taking voluntary retirement as DDGM RMC Kolkata, he joined as a faculty in the Department of Physics, University of Pune. He has spent the longest time in teaching and research in various renowned institutes, including Pukyong National University, Korea, and CDAC Pune, with core research area of dynamic meteorology, NWP, and thermodynamics. At present, he is a visiting faculty in the Department of Atmospheric and Space Science, Savitribai Phule University. He completed his PhD in quantum chemistry from the University of Calcutta in the year 1969. He is recipient of V. Bhabnarayana Award for his research. He has published more than 60 research articles in various reputed journals in the field of quantum chemistry, monsoon modeling, and QPF. He has guided 9 PhD students and had examined more than 25 PhD theses from various institutes, various universities, and few of them are Bombay University, CUSAT Calcutta, Kerala, Sri Venkateswara University, Tirupati, Banaras Hindu University, and Pukyong National University, Korea. We welcome you, sir. Thank you.
Thank you very much, Dr. Millie. Now, I would request Professor Sen, sir, to please share your screen and.
Good afternoon, everybody. Thank you, Dr. Ghosh, for introducing me. Okay, my topic of discussion is application of dynamic meteorology in air pollution modeling, forecasting, and dispersion of boundary layer. You see, when we are talking about the dynamic meteorology, there would be some, some sort of repetition, because Professor Mohanty has talked about dynamic meteorology, so there will be some repetition in the equations and other things. But what I shall do, I shall not derive any equation. I shall write the equation. First of all, I will talk about what the dynamic meteorology is. Then we'll talk about boundary layer, then pollution and the dispersion equation for the pollution. So these are my topics of discussion. Now, what is dynamic meteorology? Dynamic meteorology deals with the atmospheric motion and their time evolution using analytical approach, and that is based on the principle of fluid dynamics. Then I shall talk about synoptic meteorology. Synoptic meteorology encompasses the description, analysis, and forecasting of weather. Now, there is a lot of belief that dynamic meteorology and synoptic meteorology, they are not working together, but it's the wrong information, wrong concept. Since the numerical weather prediction models become involved in weather forecasting, the difference between the dynamic and synoptic has become artificial. So actually one is just helping the other. It's not that they are different. Now, the motion of the atmosphere has been governed by these fundamental physical laws. These physical laws already Professor Mohanty has discussed: conservation of mass, conservation of momentum, conservation of energy. So these are the forces which are acting there. They are the pressure gradient force, gravitational force, and frictional force. But one must remember that I have not mentioned here the centrifugal force and Coriolis force. We have given the only real forces. The Newton's second law of motion is referred to fixed coordinate system, but the Earth is rotating on its own axis. So the second law of apparent forces have to be included in order to apply the Newton's second law. So here we are including centrifugal force and Coriolis force. These are the apparent forces. The forces which I have told earlier, those are real forces. So the basic equations are like this. The first equation which I have written, dv dt equal to this right hand side 1 by 1, left hand side is the acceleration, right hand side first term is pressure gradient force, the second term is the Coriolis force, third term is gravity, and last term is frictional force. Now, quite often we are neglecting this F, but F we cannot neglect when we are considering the boundary layer. We are coming to that next step. Now, next is conservation of energy. That is the first law of thermodynamics, which you have given, that already has been discussed by Professor Mohanty. Then law of conservation of mass, that is called mass continuity equation or continuity equation. Then next is the combined Charles and Boyle's law, that is the equation of state. And last one which I am discussing, the conservation of moisture, that is called moisture continuity equation. Now, this moisture continuity equation means it is the total moisture in the atmosphere is constant. It is not reducing or increasing. It only changes its phase. Now, the equations which I have written, those are in vector form. Now I shall write it in the component form. So these are the three components. The first one is the x coordinate system, that is towards east, and the next one is the northerly component. For positive direction is north, and the last one, that there is a mistake here, it should be dw dt. So it is the vertical motion. And G is not only gravitational force. This is the gravitational force plus centrifugal force. And Fx, Fy, Fz, they are the friction in the x, y, and z direction. Now, if in this equation, if I assume the motion is horizontal, frictionless, and non-accelerating, then what will happen will be, from that equation, will be, if we go to the previous equation, in this previous equation, if we assume that there is no acceleration, the horizontal means the last equation is not there. Then if we take the horizontal frictionless, the friction is we are considering, that goes, and non-accelerating, so left-hand side goes. So there is a balance between the pressure gradient force and Coriolis force. So that is what is our geostrophic wind. So geostrophic wind can be written like this. Now, in the geostrophic wind, there is a balance between the pressure gradient force and Coriolis force. Now, since we are concerned about the pollution and the boundary layer, so we will talk about boundary layer. Atmospheric boundary layer, simply boundary layer, is that part of the atmosphere which is next to the Earth's surface. That means that the friction is involved. This is the theater of all aerological processes of anthropocentric importance. In the atmospheric context, it is never very easy to define exactly what constitutes and limit the boundary layer. All practical purposes, it is the air above where the influence of the underlying surface is felt. Stahl has defined the boundary layer as that part of the troposphere where they are directly influenced by the presence of the Earth's surface and respond to the surface forcing with time scale of about 1 hour to or less. Now, the theoretical descriptions are complicated because there are a lot of non-linearities, and they are non-linearities due to a variety of reasons. The frictional drag, evaporation, transpiration, heat transfer, pollutant emission, terrain-induced flow, modification, all these are non-linear. So this is a very difficult part. So now why should we study boundary layer? What is the importance of boundary layer? Actually we spend all our life, almost all our life in the boundary layer, excepting when we travel by air from one place to other. That time we are not in the boundary layer. Otherwise we spend most of our lifetime in the boundary layer. So we feel during the daytime it's rather warm and night is a little chill. Our dwellings are constructed, buildings are constructed, all commercial activities are taking place here. So we know the local breezes, microclimate. We sense the contrast when we travel to other places. Suppose we are in one place, we go to another place, there is some changes. So we just feel all this in the boundary layer. The primary source of energy in the entire atmosphere is solar energy. Actually, solar radiation, when it comes into the Earth, it is not absorbed by the air or the atmosphere. It is directly coming to the earth, and Earth's surface is heated and the heat is transmitted above. So through the atmospheric boundary layer, approximately 90% of the net radiation is absorbed by ocean causes evaporation. The evaporation amounts for about 1 meter of water per year over the Earth's ocean area. The latent stored in the water vapor is about 80% of the fuel that drives the atmospheric motion. Crops are grown in the boundary layer. Evaporation and transpiration takes place here. Pollution is trapped in the boundary layer. Fog occurs in the boundary layer. Some aviation, shipping, and other commercial activities are conducted within the boundary layer. Cloud nuclei are stirred into the air from the surface of the boundary layer process. Now, what we encounter daily about thunderstorm, cyclone, hurricane, they are just inflow of moisture takes place in the boundary layer. Turbulent transport of momentum down through the boundary layer to the surface, the most important sink of the atmosphere. Turbulence, gustiness, affect the architecture, design of the structure. Wind turbines extract energy from the boundary layer winds. Wind stresses of the sea surface are primary energy source of ocean current. Turbulent transport, advection, and boundary layer move water and oxygen to and fro from the immobile plants. There are 50% of the atmospheric kinetic energy is dissipated at the boundary layer. And so on and so on. There are many more things. Now, what is the depth of the atmosphere? This is a very difficult thing because it may be, say, from 30 meters to about 3 kilometers during the tropical area, during the summer season in the tropical region. So normally, for the mid latitude, it is taken average value of depth of the boundary layer is about 1 kilometer, and it contains about 10% of the mass of the atmosphere. Now, this also is divided, this 1 kilometer is divided into several parts, very near to the earth. So, where there is no turbulence, the wind speed is very small and flow is laminar. That is called laminar sublayer. Here only the viscous force is important. Now, for statically stable atmosphere, turbulent mixing takes place in the boundary layer is generated by the dynamic instability with the strong vertical shear, wind shear at the ground, near the ground. Turbulent mixing may be mechanically driven, thermally due to heating. It is therefore useful to divide the boundary layer into two sublayers, surface layer or surface boundary layer and Ekman layer. Now, the surface layer extends up to about 50 to 100 meters. And here what is happening? The frictional force arising play the important role, and it is independent of the height. And Coriolis force and pressure gradient force are negligible in comparison with the stresses which arise there. Density is also considered constant. Now, all this up to 1 kilometer is called the Ekman layer, or it is called spiral layer also. There is a three-way balance among the Coriolis force, pressure gradient force, then gradient force. So these three forces, the Coriolis force and pressure gradient force, are neglected here in this surface layer, but in the 1 kilometer region, that is the Ekman layer, there is a balance among the three forces: Coriolis force, pressure gradient force, and eddy viscous force. So above that is the free surface. So if we just look at this diagram, then if you just see at the bottom near the earth, that is laminar sublayer, then surface layer or surface boundary layer, then we are having spiral layer. Spiral layer is starting from the bottom to the top. It is about 1 kilometer, and above that it is free atmosphere. And the free atmosphere means we can say that theoretical. We have talked about that geostrophic wind. Theoretical geostrophic wind can be obtained there. There the isopers are parallel to the wind, but at the boundary layer itself, the they are cross isobaric. Now, what is laminar flow and turbulent flow? Now, I shall show the diagram, then it will be easier to. The laminar flow is that straight and all these things. At turbulent flow, we are seeing some circular motion and all these things, some vortices and all this we are seeing. Those are the turbulent flow. Now, what are the causes of turbulence? Mechanical turbulence, that is due to friction. Then mountain waves. When we cross the mountain, that time on the lee side of the mountain, after crossing the ridge, we say that is very dangerous for aviation purpose, but that is not our boundary layer. That is the boundary layer, mountain boundary layer. There also turbulence takes place. Then thermal or convective turbulence, that is arising due to sun's heating on the surface unevenly. Suppose we have got different types of surface. So we are having, say, rocky mountain, we are having sandy surface, but we are having grass. So they are then water surface. So they are having different effect. So convective current, all these things are set in the motion in the boundary layer. So cumulus, towering cumulus or cumulonimbus clouds are present that they start from the boundary layer and extends up to about, say, 12 kilometers, 13 kilometers. That's a normal thing. Now, lifting of warm air by sloping frontal surface. This we are not encountering in our countries, this SAMA area. Then the wind shear. Wind shear means change in the wind direction or wind speed, both horizontal and vertical distance. Wind shear, they exist in the areas of temperature inversion, along the troughs, ridges, and around the jet streams. Now, we are talking about the viscosity, molecular viscosity and eddy viscosity. Eddy means the swirl which we have seen, we have shown in the figure. Now, if we just look at this diagram, then the bottom plate is fixed, upper plate is not fixed. In between there are some fluid, and we are moving that direction of the movement, we are calling it x. And the distance between these two plates is L. So if we give some force, then the fluid will be moving with a speed, let us call it u0. Then as we come down, it will be 0 at the bottom. So there is a difference. Now, in order to make the motion, we have to give some force. That force is equal to mu into A u0 by L. And mu is the constant of proportionality. That is called dynamic coefficient of viscosity. A is the area of the plate. U0 is the speed which we are putting, and L is the distance between these two plates. Now, if we write in the, say, continuous form instead of discrete form, then we can write it T Z X, tau Z X equal to mu del U del Z. Tau Z X, the component of shear in the X direction due to the vertical shear in the Z direction. Now what this for? This is arising due to molecular motion. So now what happens? There will be, when we just see, there will be downward transport of motion, the momentum. It is moving at the top, there is maximum velocity. As we go down, it goes to 0 at the bottom. So this speed is decreasing. So the momentum is decreasing. So there is transport of momentum downward. So more than the transport of momentum in the upper direction, the upward direction. So this transport of momentum per unit time, per unit area is called shearing stress. This transport is called molecular diffusion. Now, dynamic coefficient of viscosity may be just defined as the tangential force applied per unit area, which will maintain a relative velocity of unity between the layers of the fluid at unit distance. Now, what is the characteristics of this mu? Mu is slowly increasing function of temperature. Water mu decreases with temperature. It is the opposite. The ratio of dynamic coefficient of the viscosity to density is called kinematic coefficient of viscosity. So far we have discussed about molecular viscosity. Now, what we are telling, if we are just moving the upper plate with certain velocity, then the fluid is moving and they are having the laminar flow.
No, sir, please continue.
Now, if we increase the speed, after some time, we'll see some circular thing, some bubbles are coming down. Now, that is due to that is called turbulence. So when such things are happening, that is called turbulence. And there the molecular viscosity is not important. There the dynamic coefficient of eddy viscosity or eddy excellence coefficient, that is viscosity. That is called the kinematic coefficient of viscosity is like just divide by rho. Now, when should we say that the turbulence will start? There should be some threshold value of this motion, the force which we are applying. Now, that has been given by a dimensional quantity called Reynolds number. That is the ratio of inertial force to the viscous force. When this ratio exceeds about 2000, then some people say it is 1800, so roughly we can say it is 2000, then the turbulence starts. Now, the forces we have discussed so far are this, but the F we have not discussed. Now, since the friction is important in this, so the equation of motion which we have seen has to be transformed for that. So what we are getting, if we just look at this, the equation, first equation, it is in the x coordinate system. Similarly, y coordinate system and z coordinate system can be written. Now, if we look into this, the first two terms on the right hand side were the same as the previous one in the equation, and then the third term was f. Instead of f, we are getting this portion. Now, this is due to the motion for the viscous flow, that viscous motion we are getting. So two terms are there. If you assume that it is incompressible, then the last term goes. So we are left with this. So there is an additional term, that frictional term, which we are neglecting in other cases, that is an additional term is coming. Similarly, for y and z component, we are getting this equation. Now, these equations are known as Navier-Stokes equation for incompressible viscous fluid. Now, in case of turbulence motion, so this equation, the last terms are to be transformed into this, because that is not due to the molecular motion, that is due to the turbulence motion. This is due to the, not due to the turbulence is occurring, not due to turbulence, that is the state of the fluid. Now, because of the state of the fluid, the turbulence is occurring. Now, so this gets modified. So the equations we have written on the bracket on the last term on the right hand side is like this. Now, you have written bar here. Bar stands for the average value, and U dash is standing for the fluctuations. Now, that is bar stands for the average value, that is what we are talking about, the time average we are taking. So this is called, this stress term is called eddy stress term. Last term in the bracket is called steady stress term. But strictly speaking, we should have added that the molecular motion also, that the viscous force also. But viscous term is unimportant. It is compared to this term, the viscous force is very small. So that is why we have not written that term. Now, stability of the atmosphere. The atmospheric condition is very important, the stable, unstable, neutral, or conditionally stable. Now, suppose if a parcel is just lifted up, it gets cooler and cooler, therefore denser. If the surrounding temperature of the atmosphere is more, then it will sink. That is called stable atmosphere. If it is the surrounding temperature is less than that, then the parcel will move up. That is unstable. If they are same, then it will be neutral. If some situation stable for unsaturated parcel, some situation that's unstable for saturated one. That is called conditionally unstable. This diagram will just give you an idea. Now, the left side, we are getting unstable. Now, that is the parcel. If any disturbance is given, it will just fall. It will not stay there. It will be falling. So that is unstable condition. Like say, suppose we sit here, then if we move the chair, if we just tilt the chair, there is a certain condition. Beyond that, it will fall down. Or suppose we are cycling. So when we are cycling, we are stable. But when we are not cycling, if we do not touch the ground, we will fall down. That is unstable condition. So here in the atmosphere, it is the rising condition, and stable condition means the sinking condition. It comes back to this original position. And third one is neutral. That means it does not move up or does not come down. Now, cumulus cloud, which we see during the thunderstorm activity, that is occurring mainly due to instability. And what we see nowadays, fog, particularly in the northern parts of our country or say Pakistan, all these places, that is called fog, is due to the stability of the atmosphere. Now there is another thing which is called morning-Obukhov length. The simple definition of morning-Obukhov length is that height at which the turbulence is generated more by buoyancy rather than wind shear. It is positive when stable stratification takes place, negative when unstable, and infinite when it is neutral stratification. You will be surprised to know this morning-Obukhov length, all these things are discovered in 1930s, and all this work was published in some Russian journals. And it was not known to the Western world till 1960s or 70s. So it was not known because those were in the Russian language. Now, how the wind profile in the surface layer? Surface layer means where only the laminar flow we are seeing very near to the surface. Just above the laminar flow, we will study the surface boundary layer. Then if we just see above that up to about 100 meters or say 50 to 100 meters, there the wind is varying with height with this equation that is called logarithmic law. So our U star is the surface stress divided by density, the square root of it. And it has got the dimension of the speed, and that is why it is called friction velocity. Now, you have to remember this logarithmic law cannot be applied. If you have got some tower and we get the temperature at different height, it will not be correct if we apply this equation all the time, because this is valid for the neutral condition. But logarithm law fit when the atmosphere is neutrally stable, but it is not a good description for the wind is that the atmosphere not neutrally stable. For this, we have got some several empirical law, but most commonly used is power law. Power law is given by this. By M is a non-dimensional quantity is varying between 0 to 1. And if M is 1 by 7, then it's a neutral case. This is a very good fit. We have already seen in some cases while fitting up this equation, we have seen that this law is a better fit for the wind condition in the boundary layer. Now, Ekman layer means it is starting from the bottom to about 1 kilometer. Now, here the main mechanism is by turbulent transfer. This is due to the main mechanism of heat, moisture, and momentum exchange between the atmosphere and the Earth's surface. This transfer takes place in this layer, this boundary layer. This is called Ekman layer, or this is called planetary boundary layer. Now, what are the things occurring here? Here we assume that there is the horizontal wind shear is small compared to the vertical wind shear. There is a three-way balance among Coriolis force, pressure gradient force, and eddy viscous force at every level. Eddy exchange coefficient is independent of height. density and pressure gradient are constant with height. So we get U and G in that form, where gamma is equal to F by 2K. K is the coefficient of eddy viscosity, and F is the Coriolis parameter.
Sir, 10 minutes more.
Okay. Now air pollution. What is air pollution? Air pollution is contaminant in the indoor or outdoor environment by chemical, physical, biological, radioactive agent, by production material that modifies the natural characteristic of the atmosphere. So the air pollution may be anthropogenic, that is man-made, or natural sources. So anthropogenic will be the device that we are using combustion, we call in our place in India it is called chulha. Then motor vehicle, industrial facilities, forest fires, etc. Now, then we have got the other sources, that is that carbon monoxide, ozone, nitrogen, sulfur dioxide. These are coming from, these are causing the respiratory and other diseases. Now, I have given a picture of the which is effluent coming from the chimney of a factory. This is, we can see that contains the pollution. Now there are two types of pollution. One is primary pollutant and there is secondary pollutant. This figure will give you the good idea about that. Now primary pollutant is the different sources, they are polluting this, they are called primary pollutant. Now the primary pollutant, they react among themselves and they give some more pollutant. Now say sulfur dioxide. Sulfur dioxide with oxygen, it becomes sulfur trioxide. With moisture, water vapor, it becomes sulfuric acid. So, similarly, nitrogen oxide. So nitric oxide to nitrous oxide to nitric acid, so hydrogen peroxide, ozone, and all these things. So these are called secondary pollutant. So in the atmosphere, we have got both primary and secondary pollutant. Now, sources of air pollution: industrial emission, vehicle emission, domestic combustion, agricultural activities, natural sources. Now, agriculture, these are the first three things you can understand very easily. But how agricultural activities cause that chemical fertilizer, pesticides. So, and when we are burning the agricultural waste, they give something which is harmful. Another thing, so in this part of the world, say this, our South Asian country, where rice is grown and it emits in the rice field, we get methane. So that is also a pollution. And natural sources are there: volcanic eruption, forest fire, dust storms. All these are air pollution. Now, impact of pollution, it, as you know, health is there with asthma, chronic bronchitis, cardiovascular condition. So all these things are causing their health impact. Then we are having environmental impact. The air pollution adversely affects our ecosystem. Then soil, water bodies, they are damaging the vegetables, impacting wildlife. High concentration sulfur dioxide, nitrogen oxide can lead to acid rain, which has that environmental impact. Then some air pollutants such as greenhouse gases contribute to global warming. Then acid rain can damage forest, lakes, building. Then lastly, the economic impact. Air pollution can have significant economic cost, including increased health care expenditure. Then agricultural production also may be because of the acid rain and all these things. Then the wind blows dust into the air. Automobile, trucks, buses emit pollutants from engine exhaust during refueling. Now, dispersion of pollutant. This is the main thing which we are going to discuss. The dispersion is the process by which the atmosphere mixes and transports pollutants. Dispersion refers to what happens in the pollution during and after its introduction. So the pollution dispersion takes place in many ways. It depends on the meteorological conditions, especially wind speed, wind direction, and stability. Suppose the atmosphere is stable. If there is a pollution in the atmosphere, that will come down to the surface level, and that will be say, more harmful to the health condition. The emission height, it depends on the emission height. So ground level to, say, road level to high level, all these tall chimney, then local and geographical features, then sources. Now the fixed points such as chimney or diffuse number of sources such as cars and solvents. Now, the dispersion of pollutants in the atmosphere is the result of the three mechanisms. General air motion that transport the pollutant downwind. Downwind means the direction in which the wind is blowing. So that is the downwind. And the upwind is the direction from which the air is coming. Turbulent velocity fluctuation that disperse the pollutant in all directions. Turbulence motion is taking place, so it can disperse in all directions. And diffusion due to concentration or gradient of the concentration. Now, atmospheric diffusion model. What is atmospheric diffusion model? It's a mathematical simulation of how air pollutant disperse in the ambient atmosphere. It is done by some computer programming, some algorithm. The dispersion model to estimate the downwind ambient concentration of air pollutant and toxic elements which are there. So the types of, there are 5 types of air pollution dispersion. Box model. It is the simplest type of model. It assumes that air pollution present in the box is homogeneously distributed. Hence, the air pollutant concentration is estimated within the air shed. Then Gaussian model. Gaussian model, this is the most commonly used model, and it is the oldest model, one of the oldest models. It is assumed that it is the pollutant follows the normal probability distribution. And dispersion is continuous, buoyant, and air pollution plumes originate from ground level or elevated source. Flow of pollutant is in the form of vapor or smoke in the air. Lagrangian model. Lagrangian model calculates air pollution dispersion by computing the statistics of trajectory of large number of pollutant plumes per cell. It uses a moving frame of reference and the parcels move in the initial location. It is based on fluid elements that follow instantaneous flow.
Sir, 2 minutes.
Okay, I will finish up. Eulerian model. In this case, chemical species move in the fixed direction. So it was the movement in this fixed direction that you did, and dense gas model. Now I shall tell about the box model. In the box model, it is considered it's a box. So a 3-dimensional box. It's like a parallelepiped, and the city is inside this. So it says that the concentration, pollutant concentration, air leaving the box is equal to C equal to B plus Q into L by UH. So C is the pollutant concentration, air leaving the box, and B is the concentration of air entering the box, and Q is the pollution mass and emission rate per unit area in the city, and the length of the box in the direction of the wind. We take the direction of the wind in that is we consider the city is in that direction, and wind speed is U, and H is mixing height. Then we told that the Gaussian model, we assume that they are following the normal distribution or Gaussian distribution. Now, if we consider that this is the equation for that, if we just see this diagram, if we see that the mu is the mean and sigma is the standard deviation, the curve fits like this. It's called Gaussian curve. So this is the Gaussian curve or normal distribution. So Gaussian dispersion model is like this, that we have seen that the plume is just coming in the central line and it is going like this. Now, what we are assuming their solution, source pollutant are constant wind speed, wind direction, atmospheric stability class is same. Then pollutant mass transfer climate due to bulk of air motion in the x direction. No pollutant chemical transformation takes place, and wind speed is more than 1 meter per second and limited to predicting concentration of about 50 meters downward. So this is this diagram which we are showing, that it is just giving like this. Now there are some key parameters. Now this is the condition C is a function that is concentration. It depends on X, Y, and Z and stability. So this is the term. And sigma Y and sigma Z depends on the atmospheric condition. So this is dependent on the stability and all these things. Now, Gaussian dispersion equation is this. Q pollutant emission, grams per second, H is effective height, then U bar mean wind speed, horizontal crosswind dispersion coefficient, vertical dispersion coefficient. That is really the standard deviation, you can say. Then volume dispersion equation, then ground level concentration height, where we are just taking the height is that we are just taking into consideration Z is 0, then in that case it coming out like this. Then we are taking Y is 0. We are getting, when we are taking Y and H is also 0, YZ and H is 0. Then just by simply putting there, we get the ground emission, we get that we are getting this. Same thing with just from that equation we are getting. Now we will be discussing the other type. There are two types, that is plume and another puff model. The plume is the upper one that we can see, that is a continuous, and the puff is just that discrete puff are independent of the source. And the plume model assumes the continuous emission from the source. So Lagrangian model, we are just the same as the planetary boundary as Z. This is the equation for the puff. And the puff is located at the center, whose center is X and Y, XC and YC. And trajectory ZC is the puff emission. So we get that is the puff center, the buoyancy. So this is the main difference between Lagrangian and this Gaussian, because in Gaussian we have the continuous, here discrete. Now Eulerian model is similar to the Lagrangian model, only difference that uses that fixed three-dimensional Cartesian in the frame of reference. So it is coming that dc dt equal to v dot del c plus d del square c plus s. V square c, d, V square c molecular diffusion term, d is the molecular diffusion coefficient, s is the source term measuring emission. Equation is solved numerically. Now, dense gas model, this is the last model which we are just mentioning. We are assuming the gases which are there in the atmosphere, they are dense. That means they are heavier than the air itself. So so there are three commonly models: degas model, slab model, and Hegardes model. These are the three models there for the gas model. So these are the things we wanted to discuss, and now these are the references which you can see. So thank you all.
Thank you, sir. Now I request Dr. T.V. Lakshmi Kumar and Dr. Swagata Paira to please take up the question and answer session as moderators.
Thank you. Thank you, Dr. Rohini. So now I will start the questions with the current speaker. Okay. So then I will go reverse. Okay. So the first question is dispersion of pollutants is good or bad? Because if the pollutant disperses, then the maximum area got polluted. And if the pollution not dispersed, then only one area is very much affected.
You see what happens when there is wind speed is very low, then the dispersion will take place only localized. If the wind speed is higher, then that will be going away from that place. And moreover, the stability condition is very important. If the condition is very stable, the pollutants will come down and that will affect more. In that case, it is more injurious than the cases.
Okay, so next question by Fayad. Okay, this is about the book. Sir, please explain about zero plane displacement.
Zero?
Plane displacement. There are some basic questions people are asking. What is the moist static energy?
Moist static energy means when there would be, say, moisture content would be their dry type and moist static energy. If we just consider, then in that case, moist static energy means atmosphere should be moist and the energy dissipated will not be going up if the upward motion is less. So the energy which is there reserved in this, that is called moist static energy.
Thank you. So there is a question from Ayesha Mohanty. What is the monsoon trough and how it affects the Indian monsoon?
Monsoon trough is the region which extends from the Indian region from the Rajasthan area to the Bay of Bengal. Monsoon trough is the region if we just say that is the main region of vorticity. If the monsoon trough is in the proper condition, proper area, from say Rajasthan to this, the monsoon is supposed to be say normal. If it moves to the north, then what happens? The whole moisture and the vorticity is towards the north. So the main rainfall will be remaining near the foothills of the Himalayas. Northeast India will get plenty of rainfall and all these things. But the mainland of India will be dry. On the contrary, if moving to the south of its normal position, then both the northern parts of the country, excepting the foothills and the peninsular region, they will get rainfall. There are some cases when the northern side of when the eastern side of the trough is moving and western side is not moving. That case, the local area will be affected. And that is very important, this monsoon trough, because there are several components, important components of, say, monsoon. One is monsoon trough, the heat low, which is over Rajasthan area and Pakistan area, heat low. Then we have got the upper tropospheric high pressure over the Tibetan region. Then we have got the high pressure, the lower level in the South Indian Ocean. So these are the things which are. Next is important, the low level jet. So these are the factors which actually changes the condition of the monsoon.
Yeah, thank you, sir. There is a question from Satya Prakash. How the jet streams and boundary layer are related to each other?
How
the jet streams and boundary layer are related to each other?
The jet stream boundary layer, you see, if you particularly see the boundary layer jet stream is the low level jet stream. One of the examples I'm giving. So that is helping in some condition, and say if it is in the say around say 20-degree latitude of Indian region, then the Indian rainfall during the monsoon time is good, but it moves little to the south and all these things. So that rainfall will be confined there, because there are a lot of, in this, when there is a jet stream or any strong wind, jet stream is really low level jet stream is not an example of real jet stream. Jet stream has got some function, say some other definition. So what happens? In that case, the vorticity is near that, because they have the shear, there is vorticity near there. So vorticity will cause upward motion and the rainfall. So that is the reason it is very important, this oscillation from north to south.
Okay, sir. There is another question. If in Ekman layer the air is spiral, then how can we calculate horizontal velocity of wind?
Because that calculation I have not shown. That question itself gives that. Calculation we have not done here. So calculation is shown there, because there is a three-way balance.
And there is a last question for you, sir. How exactly the boundary layer is defined?
How boundary layer is?
Defined.
It is defined just only a simple word, that the boundary layer is that part of the atmosphere which is affected by the surface of the earth. Now boundary layer means surface of the earth. Suppose we are going to the hill. That is the surface of the earth there. So their boundary layer will be from the hill. But suppose in a normal condition, in the normal road and all these things, or normal field, there the boundary layer will be have the effect of the boundary. As I have told already, because the time was short, I was told that you cut down the time. So that is why I just did not tell everything. Now it depends on the surface, underlying surface. So,
a few more questions I think participants have asked. Why Monin-Wabuko length is infinite in neutral stratification conditions?
actually, if we just use the equation, if we have got the moment, because that expression I have not given, I have just given the definition only. So that equation will show that when there is stability and neutrality and all these things, then when it is neutral, then it becomes negative, because it is coming in the numerator. The value is coming in the numerator, value is large.
Yeah.
Numerator value is large, so that is considered.
And some participants are asking about the reference book, sir.
Reference I have given, no? The last.
Yeah.
Right.
And Swagata, can you take up the questions for Mohanty, sir, or can I continue?
Yeah, I can.
Yeah, please.
I can do that. So the very first question is very, it's like a exam hall. So Coriolis force is apparent force, but still it causes deflection of air parcel to right in northern hemisphere and left in southern hemisphere. So why it is said to be apparent force? The change of coordinates. Sir, it's the question to Mohanty. Sir, you are mute.
So how we define the force? We define the force as a mass into acceleration. The force gives the motion. So that means it changes the magnitude of the speed. But the Coriolis force is not changing the speed, but it is deflating, changing the direction. And then second thing, actually, force gives the motion. But here, actually, the motion, if suppose there is no velocity, no motion, then there is no Coriolis force. So when Coriolis force arises, when there is a motion. So start with motion to force. But the body force or the main force, the force comes, the force gives the motion. Like you push the thing, then it will move. But here, when it is moving, it starts deflating. That's why it is called apparent.
Okay, sir. The same question related to Coriolis force. Does the Coriolis force really not affect the wind speed, but only the direction?
Yeah, it changes the direction.
Okay, so there are some simple question. Sir, if as per the temperature and pressure consideration, where the food will be cooked faster in high altitude or low altitude regions?
Yeah, you know very well, everybody are using every day, use the pressure cooker. If you are cooking that in open vessel and you are putting in the pressure cooker, so then you know that if you are very fast to cook, you put pressure cooker. So if pressure is more, then you go on heating and it can have boiling point. You know what the boiling point is. Generally, in the normal pressure is 100 degrees. But then if it is suppose it boil much before that, then it is holding there is not more. So that means it will not cook much faster, your all water will evaporate. But when in the pressure cooker, what will happen? We put the more pressure so that it can hold, it boiling point starts by holding more heat. So obviously high pressure things. So if you go to top of a mountain where pressure is low, like you go to Himalaya, Everest, suppose, then it is almost half of the pressure, 500 HPA. But if you go to sea level, it is 1013. So therefore, actually, as you go higher up, then your steam things boil much faster. So it is holding is not more. So cooking will be
Easier in the lower.
So it all is practical problems in the life.
So there are few questions. I don't know how it can be answered very straightforwardly. Like how all associated forces act to make dynamics in atmospheric events. How their coordination is maintained within Earth system.
Yeah, you see that actually the coordinates maintained. You see that generally actually we all are very familiar with our geometry and things that we go for Cartesian coordinate x, y, z. But the Earth is not a straight plane sheet. When we do a map, we do a projection. That means the cut at this certain point, it may be a stereotype motion map with pole, or it can be a cylindrical or things like that. So generally, being we all now dealing with the global atmosphere and so on, and we generally go as a polar coordinate. The polar coordinate means here what it comes, because if a polar coordinate system, then it r, phi, and lambda, or things like that. But whereas not x, y, z.
There are a few general questions related to climate change, all this, but I think it was not covered in today's class, so we can take those questions later. I feel so. And also one question: what is moist and dry static stability? I think when you talked about that monsoonal variation, there was a plot called moist and dry static stability. So is it possible to define quickly?
Yeah, but that we have done in summer learnings. So if they have not studied, so they should see our course on physics of the atmosphere.
Yeah. One question is good that from Anchal Goel. What is entrainment zone? How it is important to drive the cloud movement?
Yeah, you see that is again physics, but anyhow, you see that when a cloud is formed, it is only that when you have low level convergence and upper level divergence, then the air mass moves up, and then entrainment zone is that where actually air is entering in the cloud. But when cloud became thicker, because actually vapor is lighter than dry air, but when water comes, water ice, then it is heavier. So then actually, then that starts falling. But then it depends upon the drop size. If drop size is large, or if you have hills and so on, so then it starts falling. So then you get a downdraft. That is what happens in a thunderstorm type of things. First we have an updraft, then build up the clouds. When we have very tall clouds and the mass is become heavier, then it starts falling. Then we have a downdraft. During the downdraft, we get a cold winds, and you feel as if somewhere it is rain or so, but not it so, but it is a downdraft, means the air coming past through the water and this thing, and then it evaporate and become cool down because evaporation causes cooling, and so all those phenomena takes place. But it is anyhow physics of the cloud physics, and we cover that in physics of the atmosphere. And I think this would have now cross referred to the earlier lectures, because we should not. They should ask new things related to the dynamic. We want more questions from the participants. That what I told at the end, that all who are putting good questions and relevant questions.
Okay, yeah. So I'll filter that. Yeah, I'll filter that. And Rohini, also you mentioned the time. So this is question for one pure meteorologist, MG Manoj. Upper level divergence is possible even without anticyclonic rotation in the atmosphere. Upper level divergence is possible even without anticyclonic rotation in the atmosphere. Then why people talk about upper level anticyclonic motion quite often?
Yeah, you see that the Dines compensation rule is that the mass will be conserved in a column also. And though entire mass of the atmosphere is conserved, because no air is escaped from our Earth, but if you take any single column, then mass also have to be conserved. So if we go on pumping, pushing the air as it converts, it cannot go down, it have to go up. So once it go up, then actually it have to come out. If not, then actually gradually it will stop. That means if a low-level conversion taking place, clouds is forming, a cyclone is forming, then if upper level it will not diverge out, then it will be also stop the convergence. And it not necessary it is a anti-clock, it have to anti-clockwise motion, anticyclonic motion, but it may not be a anticyclone, it may be a ridge also.
So there are many more questions like El Nino monsoonal wind, but I think it is not covered today's lecture, so I am not taking. One small question from Rahul Jaiswal. The question is not well structured, but I think he wanted to know, okay, let's read that. I have a question about that. What will be the effect of increasing temperature of Earth on wind system?
Increase of temperature on wind system. You see that it is a question not properly structured as you told exactly, because temperature rise will definitely increase the holding capacity of moisture more. That is true. But then actually, it is not the temperature, it is the gradient of the temperature which gives the motion. It is not the temperature will give the motion. It is the gradient of the temperature, because gradient of temperature gives the gradient of the pressure, and gradient is pressure that gives the motion. Not that high pressure will give motion or low pressure will give motion. It is if you have high and low, then you have the motion. So motion is actually dp by dx or dp by dy. It is not p. So that's if your whole atmosphere suppose pressure is high, nothing will happen. If your whole pressure is decreased, it will nothing happen. But if high pressure, low pressure, then your wind will blow from high to low.
Yeah, I recall one sentence from your class that slope is important for anything. So yeah. So I think Rohini, there are a lot of questions, but the session will, this tutorial will be long for 18 lectures. So those questions we can get it later as well. Let's go for.
And at the end of all the lectures, perhaps we can have all the speakers, and if pertinent questions people ask, and those who ask really very good and innovative questions, we should give them appreciation also, so that let them think over. Because this is a dynamic methodology. Unless you think, unless you visualize yourself, the coordinate system and other things to be very, very difficult. I don't know Somnath will face what type of problem. When you go to coordinate system and all these things and derive the equations. So I feel that it may not be possible for everyone, but the bright students, they should think about, they should draw themselves, they should visualize. I know that it is very, very difficult to show you the three-dimensional globe, and over that the motion is there and rotation taking place. But I think each student should do that. But a lot of references are there, very good references there, and already Professor Sen has given a very good compile of those. All book is very good for the boundary layer, and Holton and Hattie Martin, they are very good for the dynamic meteorology, and though they are very ancient. Hayes is a very good book. That is the first book I read to enter to atmosphere science, because Introduction to Theoretical Meteorology is a very good book. So a lot of very fundamental books are there. So I feel that and many books are now available as e-books also, because students, they know how to download those things, and because it is not ethical to share the download material without permission, so they can do themselves and go through. And I think if our president and secretary agree, we should encourage the students that those who will ask very good, relevant questions, that means they have better understanding. And we encourage the students, they should have more and more curiosity to ask understand the questions, try to solve themselves, otherwise ask in the class. And just for the sake not to ask. And also, as I told at the end, perhaps all the lectures, we can have a very good panel discussion type, maybe one lecture, question answer by students and speakers.
Okay. So Lakshmi, I think we are not going to get any more questions. There are a lot of queries about that speech by the secretary. So will we, because of that time the volume was not perfect. will you again, maybe it would be better to share for 3 minutes.
Yeah,
What-
we will try to share it from our screen. So let us see if we
Yeah,
can.
because a lot of query came that volume was.
Namaskar and good afternoon. It is a privilege to address this distinguished gathering on the occasion of the lecture series on atmospheric dynamics and its application to climate sciences, jointly organized by the South Asian Meteorological Association, that is SAMA, and Savitribai Phule Pune University. It is indeed a very good initiative by both SAMA and Savitribai Phule Pune University. SAMA, with its commendable efforts since 2020, has become a beacon for advancing meteorological and applied sciences throughout South Asia, fostering collaborations among 9 nations. With over 700 members and impactful initiatives, including training, workshop, webinars, and lecture series, SAMA continues to contribute significantly to capacity building and knowledge dissemination across the region in terms of meteorology and atmospheric sciences. The collaboration with the Savitribai Phule Pune University, a premier educational institution known for its excellence in atmospheric and space sciences, add immense value to this initiative. Savitribai Phule Pune University's pioneering contributions, including the first MTech program in atmospheric science and its close association with the leading organizations like Indian Meteorological Department, Indian Institute of Tropical Meteorology, and so on, have positioned it as a leader in atmospheric research and educations. In an era where climate change and environmental challenges dominate global discourse, the importance of understanding atmospheric dynamics cannot be overstated. By teaching atmospheric dynamics, we empower future scientists and policymakers with the tools needed to understand and address the consequences of climate change. This subject is inherently interdisciplinary, tying together physics, mathematics, chemistry, and environmental sciences. This lecture series, running from January to July 2025, promises to delve into the complex mechanism driving atmospheric motion and their implications for weather and climate systems. Covering a wide array of topics from fluid dynamics and wave theory to the El Nino and Southern Oscillation and advanced climate modeling, it aims to equip participants with the foundational and advanced knowledge essential for tackling pressing challenges in climate sciences. I wholeheartedly applaud SAMA and Savitribai Phule Pune University for this collaborative effort to bring together experts, students, and professionals. Such initiatives are need of the hour for this region, also critical for nurturing next generation talent and driving innovation in atmospheric sciences. I am confident this series will benefit to many and pave the way for impactful research and solutions in our collective fight against climate change. Thank you, one and all. Namaskar.
So, Rohini,
Yes.
yeah.
So now I request Dr. Mohan from Bangladesh to please give vote of thanks.
Mohini is also
could you please share?
Yeah. PPT needs to share. Shall I? Rohini shared.
Can you hear me?
Yes.
Okay, thank you. Yeah. Honorable Vice Chancellor, distinguished guest, esteemed speaker, and dear participants, it is my privilege to deliver the vote of thanks on behalf of the South Asian Meteorological Association and Savitribai Phule Pune University SPPU for today's inaugural session of the weekly online lecture series on atmospheric dynamics and its application to climate science. Firstly, I extend my heartfelt gratitude to Professor Dr. Suresh Gosavi, Honorable Vice Chancellor of SPPU, for his gracious presence and inspiring opening remarks. Your support and leadership have been instrumental in making this event a reality. I also express my sincere appreciation to Professor Dr. Someshwar Das, Secretary of SAMA, for his unwavering commitment and warm welcome that set the tone for this occasion. A special thanks to Air Vice Marshal Retired Professor Dr. Ojit Tyagi, President of SAMA, for his insightful address, who is of collaboration and in advancing meteorological science in South Asia. I am profoundly grateful to Dr. Kamaruzzaman Chaudhary, sir, Vice President of SAMA, Pakistan, for his valuable contribution and for sharing his expertise, fostering regional cooperation. Our deep appreciation goes to Dr. M. Ravichandran, Secretary of Ministry of Art Science, India, for his encouraging message. It reinforces our shared commitment to scientific excellence and innovation in atmospheric sciences. To our speakers, Professor Mohanty sir and Dr. Pundendu Nath Sen, I extend my sincere thanks for the enlightening lectures. Your presentation on atmospheric dynamics, climate prediction, and air pollution modeling are both thought-provoking and enriching. Next slide, please. A special thanks to Dr. Swagata Paira for introducing Professor U.C. Mohanty sir and Dr. Miligosh Nilala to introducing Professor Dr. P.N. Sen sir. I would also like to thank our moderators, Dr. T.B. Lakshmi Kumar and Dr. Swagata Paira, for skillfully guiding the Q&A session and ensuring engaging discussions. To our program convener, Dr. Rohini Bhawar, your dedication and meticulous planning have been pivotal in orchestrating this event seamlessly. On behalf of SAMA, I also extend our sincere gratitude to all involved in the lecture series. A special thanks to our convener, Dr. Lakshmi Kumar, for the SAMA and SRM lecture series on atmospheric and climate sciences. Dr. Swagata Paira for the SAMA and BIT master lecture series on satellite meteorology, and Dr. S. Avilash for the SAMA and QSAT lecture series on radar meteorology. All of your leadership and expertise are instrumental to the success of these events. Finally, I am deeply grateful to all the dignitaries, participants, and team members who contributed to the success of your presence and enthusiasm are driving forces behind the success of this initiative. Thank you all once again for making this event memorable. We look forward to your continued support in the upcoming session of this lecture series. Thank you. Thank you so much.
Thank you.
Thank you, Mohan.
Thank you, Dr. Mohan, who is the Joint Secretary also of SAMA, and he's from Bangladesh, Naomi. So I just wanted to, before ending this lecture series, wanted to tell that the number of participants were around 350 from Zoom and YouTube, actually greater than 350 from 27 countries. And we had put a small question about how did you find the lecture series. So greater than 260 participants have rated it as excellent and very good. So thank you, everyone. Kindly keep watching the lecture series and gaining more knowledge. And also your attendance is also important. So even if you email us, we will be considering your attendance. So, sir, anything else? Dr. Swagata and Someshwar Das, sir.
No, thank you, sir. Thank you, sir. Is there. Yeah,
Almost.
thank you, sir. Is there. Yeah. No, I don't have it. So you
Almost
Taggy, sir, yes, I will ask. But if anything else we want to tell the participants from.
No, the only thing is that question answer. If there is an anonymous name, we may not take the question answer.
Okay.
Yeah, because sometimes they ask some different questions. Yeah.
You can stop sharing the.
As I suggested, Swagat,
Yeah.
every lecture, find out one or two best question, participants who are giving very interesting and thought-provoking questions.
Yeah, I'll write it down, sir. Okay, I'll take
Yeah,
your.
so that at the end, when you are giving some certificates, we can give them appreciation. So that gives them to think, not to hear only. Think on the subject and submerge them, because dynamic is without thinking and without working themselves. Gradually it will be difficult for them.
Yeah, like today's question, I think I like MG Mono's questions. Yeah.
Rohini, stop sharing the screen.
Yeah, can you stop sharing the screen?
Sir, I have a suggestion. Maybe I can tell here or not.
Sure.
Probably the speakers can give at the last slide some kind of exercise or some questions also. Open questions to the participants.
Yeah.
Before they come to next
actually,
lecture.
Yeah.
It will be useful to act as a prerequisite also.
Adding to this, there was a query like if some assignment will be given or something like that.
Yes.
So maybe instead of question, because we will already be having exam, if they can give some kind of like deriving or assignment, the speakers, it will be great. Yeah.
Yeah, that's a good suggestion.
Very good idea. Yeah.
So last slide.
We should make them to work. Actually, that is most important.
Yes, sir.
So that they can, you say only their involvement there. Our resource persons, they will put a lot of time, and we want that the results should be some fruitful results. So,
assignment is a good idea because that will make them thinking also.
Yeah.
Yes, sir. So there was another question that if these presentations will be shared or not.
Yeah, you share, no problem. Yeah. I think no lecture is actually, because this is our text lecture type.
We used to send, sir, actually, right? Every lectures after lecture.
Sir, yeah, I will email so that I can get the presentations and I will share it later then with the participants.
But I think YouTube already there. Well, they will have this thing. But in addition, if you feel to share with everybody the lecture series, that's okay, no problem.
Okay, sir.
I think YouTube is okay. For example, sir, there may be many resource person who may deliver their talk using blackboard itself, that is a computer board. They may not take the class using PowerPoint. So that time the PowerPoint sharing is not possible, no, sir.
Yeah, Somnath is giving maximum lectures perhaps out of everybody.
Sir, mostly all will be board only.
Yeah, okay. So that's why we should consider his restrictions. So I think YouTube is the best way to get for them.
Correct.
Okay.
Watching YouTube is the best. Also, in a recent meeting, some people have suggested that we should try to cut down the initial formal welcome, too much of welcome. Inauguration talk, so it's okay, but next talk onwards we will cut down all those formal things or try to minimize as much as possible and just have the lectures and then the question answers at the end. And vote of thanks, maybe short vote of thanks will be okay, but we will have to shut down after that because if we start at 3 o'clock, it should go maximum up to 4:30.
Yeah, by 1.5 hours.
Yes, sir. Yes.
So that's what we should do.
So,
today also is 6 o'clock.
Maybe we'll prepare an agenda similarly, sir. We will send for your approval. Yes.
Yeah, so finally, I want to say something from Taggi sir.
Is becoming very visible.
Yeah, we can see that.
So one more photo.
Yeah, one more photo we should take.
Yeah, and
everybody please switch on your camera.
Dr. Mohan, please.
I am traveling, actually, I did not hear. Regarding what?
You switch on your camera.
Yeah, I saw
just for a quick picture.
Your sheet color is red one. Yeah.
Oh.
And Dr. Abdul Mannan.
Dr. Abdul Mannan.
Looks like you are.
You have not given your consent for delivering lecture. We will give you a reminder also. Dr. Mannan, are you audible?
I think he is not nearby because the course has around 3 hours. So now let's take the picture. And Somnath sir, आप थोड़ी कैमरे की तरफ, yeah. But who is taking?
Ashwin is taking. Yes. Okay.
Great. Thank you.
We will get.
Okay. Thank you.
I know it is more than 3 hours, but we usually will not talk after vote of thanks. But today I want something from Tagi sir. Yeah.
Yeah, we should have 1.5 months.
Yeah.
Sir, you are muted.
Okay. Sorry, I couldn't join with my photo in the beginning. One of the suggestion was before we started this program that many of the students may not have vector and those background info.
Yeah, but I think they have a lecture. One lecture is there on vector algebra.
So can we have not the lecture, but there's some easy to understand background or training material available that can be posted, and we can tell students to go through that.
Because that's a prerequisite. Because I think there's a good book on vector, and I think Somnath must be knowing. IMD they give vector algebra first, so that need not taught in the class, but we can distribute.
Yeah, preparatory material of 3-4 such lectures, differential equations, basics of that, or vector, something which
and rotation of axis and all things, which is actually part of the dynamics, but not dynamic meteorology.
Our third lecture is on vector equation of motion in an absolute and rotating frame of reference by
already there. Very good.
इसमें correlation course आ जाएगा, but that's good. But vector algebra, partial differential equation, rotation of the axis, some standard things. Whether actually we can give that thing, people should prepare, not that to teach that.
Everything cannot be taught in this online lecture series. People have to read themselves. Can give some guidelines. Like third lecture is for the vector equation of motion, and then the students should learn from the guidelines given by this speaker. Or if they need some more help, they can send by email their further questions that can be answered to help them.
Background material is available for everyone to refer. You see, there are 1,000 odd students are there. Everybody is not attending. But if this is available, 3-4 topics being covered, basics of that, there is no harm. You may cover even the first lecture on vector dynamics. If somebody has got some initial background knowledge, then he'll pick up much faster. Otherwise, it will be totally overhead transmission. So just think of if these are readily available, don't have to some basic material, then I am sure IIT may be having such preparatory lectures, background lectures that can be shared.
Just a brief course type. It is brief thing, and we can give them. They will study themselves.
Sir, may I?
Yeah, please.
Sir, actually in every dynamic meteorology course, before starting, I take about 10 classes on whatever Tagi sir was telling, that and Mohanty sir was telling, that vector, then the differential equation, etc. But sir, problem is, sir, I don't have the note. Actually, I used to take in the blackboard or this board. So the material is not there. But if
but Somnath, if you can give something, perhaps this Rohini and their group, they can type it nicely and make it available, because you see that is a reference for them, but it is not a class.
I don't have. That's why I'm telling you, I don't have actually. I generally instantaneously in the class I take. I don't have the material. Actually, once he told me also.
But I will see if I have old material. I learned from IMD training program about vector algebra, but it will be my handwriting and this thing. So if Rohini, you can type it nicely and circulate, so maybe it will be helpful. But it is, as I told it, in 1972 or 73, it is that what we were taught by very eminent lecturers from IMD that time. So I will sort that and share with you.
Definitely, sir. Yes. we
Great,
will
sir.
do.
Great. Old is gold.
Oh,
And
Yeah,
no,
exactly.
I missed that. I think Someshwar sir had some notes, isn't it?
Dr. Datta, well, I mean, I had some old notes, of course, handwritten things long ago. But I
Yeah,
was
we
asking
can give. Yeah,
Dr.
we can
Datta,
give to Rohini, and you can give one of your good student research scholar or somebody. So because they will be future teachers. So
Yes.
do
let
you
them do
use
that thing.
electronic
Don't
board?
spend your time, but tell them to work, because our students will give many things to learn by doing the work, and that you can take help of your students.
Yes,
Dr.
sir.
Datta, do you use this electronic board for writing the equations? Do you
Yes.
use? Are you used to that?
Yes, sir. I used to that from 2020. I am used to that only.
Oh,
2000
actually, that is
बढ़िया
actually Corona benefit.
Corona effect.
You can teach by writing on the Wacom board. I mean,
Yes, yes, yes. That's why I'm telling, if you give me one class for this vector, one class, then it is I can make them all right. But
Let us not make spoon feeding by giving
let them do. Let them do.
Yeah, let them do think, because that is a fundamental thing. This basic understanding.
Sir, just a minute.